today we have Professor Prather here, our first guest. We're so pumped.
Me too.
Whenever you agreed to this, I was just so ecstatic. I've been ecstatic ever since.
Yeah, very honored.
Cool. And one of the reasons for that is because, I believe that you're one of the professors that sort of helps guide students' curiosities. And maybe not guide it, but allows them to be curious. You're just very open. You're excited to hear what people are curious about.
Yeah, absolutely.
And you were my statics professor. I believe it was either my first or second semester. And that class was tough. You're a tough professor. I'm sure there's...
I'd rather be tough than too easy,
Are you teaching statics this semester?
I am.
It's
been about a year, and I'm back teaching statics again.
Okay, nice. Yeah. So I'm sure there's students cussing you right now.
Hopefully not. Maybe in about a week.
Not
this early in the semester.
Yeah. I wouldn't say I was necessarily upset. It's just, I had to think harder.
Well, I think it's one of those first classes that you have to, especially out of high school. Maybe you're good at physics. You've been doing stuff like that, and you're used to it. Statics is kind of one of those first classes that really takes a lot of extra effort. You might understand it, but unless you go out and practice and solve the problems yourself, you can look at a problem and be like, I think I know what I do. Yeah. But until you do them, until you actually apply it, it's not that easy. So I think it's one of those first classes that really takes a little extra effort.
It's definitely tough, and that's for sure. Do you, I wanted to be super ready and have an introduction for you and everything, but if you don't mind introducing yourself.
Yeah. My name is Cole Prather. I don't go by any special titles, although I do wear many hats. I don't have a doctor, so I don't have a PhD, so I'm not a doctor, but I got my undergrad and graduate degree from UCO, so I was an engineering physics major. And then when I graduated undergrad school, I just felt like I didn't know enough, I felt like if I was going to go into the workforce, maybe say with an ME or an EE degree, I'd probably have a better shot because I'd maybe be a little more specialized. But I liked physics so much that I felt like I needed to know more before I went and got a job. So I went to school for graduate school from 2018 to 2020, and at UCO as well. And I think that was probably the best time of my life. I still, if I could go back and do thesis all day, every day for the rest of my life, that's what I'd do. Because what I was fortunate enough to do, took me an extra semester, but I was able to do my thesis as kind of it was really the only class that I was taking at the time. I took technical writing the second semester so that I could really just focus on writing my thesis and having a little bit of technical writing background to kind of reinforce the thesis itself in terms of writing standpoint versus just the theory. That was probably the best time of my life, just doing thesis tracks. So anytime anybody's like, I want to go to grad school, I'm like, do it.
Nice.
I'd say they, as if they is some figure. But in grad school, you're just treated like an adult. And in undergrad, college should be a kind of an adult thing, right? But there's busy work, there's homework, there's so many exams to study for, so many projects to do, so many different things that are keeping you busy. But in graduate school, you're really just taking classes that you're focused on, maybe that you're actually interested in, right? Because undergrad, there's all these classes you have to take, and some of them you may not really be too keen on. Graduate school was the classes that I took, the professors that I had, the people that I worked with, the colleagues I had. Definitely, if I could just go back and do that forever, I'd do it forever.
Wow, that's amazing. So, I guess because I know Albert is extremely excited to talk about your gravity research and things like that.
And your thesis, I'm very curious about.
We can talk more about it for sure.
But I thought that maybe it would be fun and interesting to first talk where that curiosity came from. So maybe I don't know, maybe a little background, where you went to high school, where you grew up, and then sort of how you got into physics.
Where did you get that spark from?
And and where did you get that curiosity that we all sort of have that's just unwavering?
Yeah, no, it is unwavering, and it's almost sometimes unsettling. It keeps you up at night sometimes. But I think really looking back, I'm glad you mentioned elementary school, middle school, whatever, high school. Because the first time I really realized I was into science, not necessarily physics, because I was, I think, in fourth grade at the time. I was going to Cassidy. There's a private school here in Oklahoma. So just a little bit of backstory. I went to Ralph Downs Elementary, Oklahoma City, Putnam City schools, and went through first through third grade there. And then my dad got a new job at a new church. And all the people at that church were mostly sending their kids to private school. And so like, hey, you know what, you should send your kids to private school too. So for 1 year, my sister and I went to Cassidy. And it was a little jarring because, you know, I went from a public school where we all were kind of pretty even in terms of the socioeconomic strata. But then when I went to Cassidy, I was certainly not, you know, I didn't have a dad that made it, you know, run a business, owned a company, anything like that. So I was kind of at the first time in my life really realizing I was kind of an outsider, and I was okay with that. At Putnam City schools, you just had a regular, you know, wear whatever you want, but there was a uniform, a dress code at Cassidy. And I remember being like, ugh, what's that about? Yeah. Right? Like, we all have to dress like the same gray blob. And so there was kind of this, probably without even realizing it as a fourth grader, thinking, man, what is this about individualism that I'm so interested in? Kind of going outside the standard norms. Well, the best thing about Cassidy was not necessarily just there's a lot more money in that school, so there's a lot, you can probably get teachers that you can pay more and can have more resources in the classroom. Well, there was a guy named Mr. Windsor, and Mr. Windsor, he taught a chemistry class. And I'm in fourth grade, I don't know about chemistry, it was really like a physical science class. But after school, he had this, I don't know what it was called, but it was basically a science club. And I remember asking my parents, hey, can I stay after school to go to Mr. Windsor's science club? And I'll never forget this because it was, you know, I'm just interested and passionate about science. And Mr. Windsor, he had this test tube set, like just, you know, blank test tubes. And I asked him if I could like mix stuff in them. I didn't even know what I was going to mix. I just wanted to play with it, right? I'm in fourth grade. I have no idea what I'm doing. Yeah. Well, he'd let me take a whole set of test tubes home. And I just, you know, my parents were like, what are you doing with these test tubes?
Super trusting in you.
Super trusting. And so I kind of had this connection with him that he kind of, you know, would, as a fourth grader, it's not like a mentorship, but he would always kind of talk to me in the hallway. We'd always talk about science. And I remember the end of the semester, my parents gave me this, I don't know if it was for my birthday or for Christmas, but I got this like anatomical, like kind of see-through, you could see all the different human body parts, right? Yeah. And because I kind of had this relationship with Mr. Windsor when I was leaving Cassidy. So I was only there for a year. For those of you who know anything about private school, it's not cheap. So I wasn't able to stay there for very long. I was there for 1 year and then went to Deer Creek High School here in Edmond. But when I was leaving, I gave Mr. Windsor that anatomical human with all the little pieces in there. It's kind of like an exchange. Like, hey, thank you for being such a cool, kind of a motivating force for me in fourth grade without even realizing it. So that was kind of my first glimmer that I like something about science is stimulating. And then there was also a rocketry club, so we would launch rockets. So it was all this kind of after school stuff in fourth grade. And then when I went to Deer Creek in fifth grade, it was a little bit of a shock too, because in Cassidy in fourth grade everything's a year ahead. So when I went to fifth grade, I was almost like doing fourth grade again. So it kind of set me back, but it was to my own benefit. Because all of the math and science that I had accumulated in that 1 year put me a year ahead when I went to Deer Creek. So I was already kind of a year ahead in math, a year ahead of science, and it just, that momentum continued. And so when I got to high school, I was taking those kind of advanced math classes, AP physics, stuff like that. And I think I'll never forget, maybe if you ever watches this at some point, there's a guy named Shane Martin, who was my physics instructor, teacher, I guess, at Deer Creek. I believe he teaches at Francis Tuttle up here in Edmond now. But what I'll say about his class, I'll never forget this. We always do, in any class you take in physics, always math, always problems you have to solve. Well, we had 3 projects in there that really kind of made me think, okay, there's more to it than just solving problems, right? Yeah. I mean, solving problems is a big part of it, but it's also about asking the right questions. And so we had this project with a hovercraft. And we made a hovercraft out of 3 leaf blowers, right? So we basically took this like kind of circular block, a chunk of wood, we wrapped it in a sheet, and then we shoved 3 leaf blowers down in some holes.
That's awesome.
And did it work?
It worked.
Wow.
If anybody finds me on Facebook, you might be able to find that video.
Really?
But we were at my buddy Zach's driveway, and it was me, my buddy Zach, and my buddy Brady. And I was a tiny little kid at the time, maybe 135 pounds, long hair, long scene. I used to straighten my hair. Yeah. So there's a video of me, a little emo kid, pushing my buddy Brady around, because Brady at the time, he played football, he's a big dude. And we were like, this is a joke, right? But if the hovercraft can lift Brady, then we'll be good, right? Because I'm 135 pounds. If it can lift Brady, it can lift me. Yeah. So we let Brady be our kind of extra weight. Yeah. But it was funny because, we have 3 leaf blowers, and he was floating around the driveway.
That's wild. That's crazy.
And so
I would imagine, just thinking about it, I would think you would need more. But
it was.
These were gas powered.
They were gas powered. Yeah. But we were all shocked that this thing worked. Yeah, and weird. They had, I can't remember how many other groups there were in our. Maybe there were 18 students in this AP Physics class. But we went out in the parking lot and tested them. Well, the parking lot, opposed to a kind of a poured concrete driveway, right? Smooth to an extent, concrete. But in the parking lot, it's gravel. And so the gravel parking lot with those kind of extra knurls in the, the poured rock that they use, the asphalt or whatever it was, it ripped up our hovercraft. But we took it to school, we demonstrated it, and so that was one of the projects we did. We also did a rocket, which is also on my Facebook. So, you go to Hobby Lobby, you buy those little rockets, you set them up, have a little timer, not the timer, but the ignition system, right? And then there it goes. So we had one of the projects was every team has to make a rocket, and whoever can make it go the farthest or the highest. I don't remember how we measured highest. I don't know that we really could. But we were out in the football field, and we were like,
unless they're only going 5 feet,
Well, we didn't have any type of, nothing to track it with a laser, no altimeters or anything like that. But the funny thing was, so, every group has their little rocket, and we did ours. But because we were always extra, me and my buddy Zach and Brady, we always wanted to just take it another step, right? It's like, okay, we satisfied the deliverable, but what else could we do? So there's these giant, you think about a cardboard roll, like on your paper towels, a little cardboard tube in the side. Well, for big reels of wrapping paper, they have these giant, maybe about 3 foot long cardboard tubes. And they're much heavier than your standard, paper towel roll tube or toilet paper roll tube. But we thought, well, how many rockets would it, or not rockets themselves, but how many little boosters would we need to buy to lift this off the ground? Because, your little kit rockets, they don't weigh maybe even a pound. They're probably a couple ounces. But this big cardboard tube, it's probably a good 1/4 inch thick. It's thick, it's heavy.
Wow.
And so we thought, well, how many rocket boosters do we need to get this? So if I remember the number right, or the letter, when you go to Hobby Lobby or whatever, they've got A series, B series. I think they go up to H series. Yeah. And the bigger the A is smallest, H is the largest. I'm sure you could buy bigger ones online, but we're 17 years old.
To be don't discount Hobby Lobby, dude.
Oh, absolutely.
There is so much at Hobby Lobby.
Oh yeah. Well, I used to work at Hobby Lobby, so I knew this, and so I was like, well, let's just go. We can go buy these little rockets. I think they sold a 6-pack, so we took, maybe it was 7. I can't remember. But if you imagine, I think it was 6 because we formed a hexagon with them. But we had, I think, the H series rockets. We strapped 6 of them, tied them all together, hit the ignition. And we're out there, I want to say it's November, it's cold. There's a video on my Facebook of it. And we've got this giant rocket. There's cardboard fins on it. We've duct taped a cone on it. We stuck pictures of all of our faces on it. if you got a sponsorship or something. Yep. So we all had all of our team members' faces on it. Another guy on our team was Peyton. But we went out there and everybody did the regular rocket launch. And we won the normal rocket launch for the farthest distance. But then we were like, hey, we have this kind of bonus rocket that we want to launch. We didn't think it was going to work. Yeah. And the video, I wish I could pull it up, but it's sitting there. It's probably about 5 feet tall. So pretty big rocket compared to these little foot-tall things that everybody else is launching. We hit the ignition switch, and Shane Martin's like, everybody back up. Thinking this thing's going to just blow up. He's like, what are these kids doing?
Safety first.
Well, yeah, and I was just like, how close can I get? Yeah. Well, as soon as it kicks off, you just see this thing just creep up off the ground. It maybe gets a foot in the air and then just keels over. But the fact that it got off the ground, you can hear it in all of our voices. We're just like, oh my God, like it's actually lifting up off the ground. It didn't go anywhere. Yeah. But just that kind of
that progress
and just thinking like, what could we have done? Right? It's like, okay, this is what I need to do, but what's possible? Right?
How can we get there?
Right. How do I get this big old thing off the ground? And so that was awesome. Kind of the second project. But anyway, I could talk more about all that. But in high school, that was kind of where, with Mr. I just told you, Seth Windsor. Seth is his son's name, Mr. Windsor. I can't remember his name, but Mr. Windsor was kind of that first science teacher that really just kind of got me stoked for
science,
figuring things out, like
That's
asking
awesome.
questions.
Yeah.
And then in high school, Mr. Martin with physics, and he's a big reason why I teach now. So.
That's awesome. I never really had like a good science teacher, like in elementary school and in high school. I was also like focused on a lot of other things though.
Yeah.
So maybe if I did, I wouldn't see it. I don't know, but I just think it's really interesting though that you found it early, right? Because like for me, I found it late. Albert found it early, but. It just goes to show, like...
Well, it's also never too late, right?
Yeah,
exactly.
That's the best part about science, yeah.
Exactly. And so, like, how do I say it? So how did you get into gravity?
Hello, space travelers. Want to look sharp while bending space-time? We've got brand new Physics Society t-shirts. The clean graphic tee is just $20, and if you want to drop some Einstein-level wisdom on the back with this quote, "I have no special talents, I am only passionately curious," that one's only $25. Rep your curiosity, rep the cosmos, and support the Physics Society. Grab yours today before entropy takes over.
Okay, well, and I'm glad you asked that because you mentioned that earlier in the question, because I think after high school, I wasn't thinking anything about gravity. I was like, gravity's gravity.
Yeah.
What questions do I have to ask about that? Just stuff falls. Well, when I was in undergrad school, I was taking a class called Modern Physics, and it was my first class.
I'm sorry.
Yeah, go ahead.
Like, I don't know. Like, to me, gravity, it's like, okay, cool. Like, but then you start to like go down that rabbit hole, and if you're the curious mind, right? Yeah. It's like infinitely confusing to me, anyways.
It feels paradoxical in a way.
Yeah, exactly. And so that's why I'm sort of curious how you found gravity, because like to me, until I really ran into you and you were like very interested, very excited, very curious about gravity, and the research you've done is really interesting, and I'm just like, I don't know. I just it's one of those things that I think most people would just be like, oh, okay, cool, gravity, like,
right?
They take it for granted, kind of thing.
Yeah,
well,
exactly.
And I think I did for even I mentioned this modern physics course. I think because I had started out in college doing graphic design, believe it or not.
Oh.
And because when I was in high school, we were talking about getting all these cameras and stuff set up. I was in the media club at school. So I did all this stuff and thought, well, I did AP calculus. I'm never going to do math again. Who cares? I'm never going to do physics again. And then I was in graphic design. I thought, this isn't for me. I miss solving problems. I miss asking questions. So I switched to physics, and then a couple of years later, semesters later, I ended up taking modern physics with the guy named Dr. Wilson, Dr. Weldon Wilson. And that was the hardest class I had taken at the time, because we did this whole, time dilation, length contraction, stuff like that. What's proper time? And I remember, I don't think anybody in the class got the proper time question correct on the exam. And I remember going to his office and like, well, what's the right answer? We had this long discussion. But I realized that there was something unique about him, about the way he asked questions and just structure his course. And so I took any class I could take with Dr. Wilson, and probably took, a good 10, 12 classes.
Can you maybe speak to that a little bit? Like, is there something like specific about the structure or something that you were just...
there is something specific. In college, a lot of times you've heard of curving exams or curving the grade of the course. Well, Dr. Wilson had a very interesting way of treating his course. You can kind of think about this as a kind of a math example with least common denominator and greatest common multiple. And the idea, what I mean by that is, I could think about my students or my class as I want to make sure that nobody's left behind. I want to make sure that we're all on the same page. but the other side of that is, what if that is kind of like your greatest common multiple? But what's also the least common denominator? So imagine I've got a multiple lane highway, maybe 6 lanes, right? 6 students. Dr. Wilson taught his class in such a way that you had your own lane. You could go as fast as you wanted. There was no, oh, I finished the problem, I figured it out, now I'm done, right? Kind of like I was talking about with high school. It's like, well, yeah, we made our rocket, but what else can I do with this?
Yeah.
So Dr. Wilson would say, nobody's going to make a 100 on the test. Because he wasn't trying to just see, oh, did you memorize all these formulas, and did you study last night, you know how to do this one problem, and that's it. It was, I want to give everybody the freedom to go as fast or as slow as they want in the class. And so rather than trying to make it like a one lane highway where everybody's got to go, if so-and-so's going this fast, well, everybody behind them has to go the same speed, right? Which is, I think, good in high school, maybe in middle school and stuff like that, where you don't want to lose anybody in the class. But I think college demands a little bit more of the student, that you have to put in the effort yourself. And if there's a student in the class who's making 100 on every exam, well, I need to make the class harder, because that means that student understands everything, right? So the idea is I want to set the ceiling so high that nobody can touch it, but not so high that nobody couldn't reach it, but just so that it's not like, oh, well, everybody's going to be making C's and B's. Or
what if that guy's just a genius, though, right?
They make the class harder. Because if they can figure it out,
yeah,
there's some other people who probably could.
Yeah.
They just may not be putting in
And
effort.
that's the person you should go cling to, right? You should go, say, how did you make 100 on this?
And I think that's also something that as a student is hard. You see the kid in class, and sometimes there's a stereotype of, oh, don't raise your hand. It's like nobody wants to raise their hand because they don't want to assume that that responsibility or power. It's like if I said 2 + 2 is what? Nobody wants to raise their hand because it's like, oh, I don't want to act like I know everything. So there's kind of a paradox in that in of itself. I'm fine with even answering and being wrong. If I raise my hand, it's like, I don't want to be wrong, and the whole class is like, oh, that kid's stupid. Keep your mouth shut.
Yeah.
Or the kid is like, do we have homework due tomorrow? Right? It's like the two sides of that.
Two sides of it.
So for me, Dr. Wilson's structure, back to that question, right, was more about, how can I make sure that the standard deviation doesn't exceed the limits, the bounds of the course? So that if somebody's brilliant, they might make a 95. But if they're making a 100, then I need to add something that's more challenging, right? I don't want the challenge to be achievable. That it's a challenge for a reason. And so for me, that was a really kind of opened that. It wasn't just, okay, I made an A, and I'll be honest, I made a C in modern physics. But it was one of the best, at the time, the best C I had made, because I spent so much time trying to figure it out.
Yeah.
That's awesome.
And that's what I respected about him. It wasn't just, oh, yeah, you study the book, you do the homework, you're going to make an A.
Yeah.
You had to put in the effort to earn the grade that you got.
So this opened you up to gravity, like to
So
want
yeah,
to explore.
yeah. So and the gravity comes in with Dr. Wilson, because I had kind of, any class he taught I wanted to take. Well, in undergrad school, I think the last semester I was taking, a couple of us, maybe 6 or 7, really, really wanted to take a class on general relativity. But we don't offer one at UCO. But there's one person on campus we knew who could teach it. And Dr. Wilson could do it. And so we asked him, we said, hey, would you, be willing to teach a class on general relativity? And he's like, well, we could do it as a seminar if, you get enough of you guys to enroll.
Isn't that who they were talking about bringing back for quantum computing or something like that?
Maybe so. I know James Chancellor does a lot of
Chancellor,
that's
who it was.
Well, he's got a computer science background, so
okay.
And I went to school with him too. I took classical mechanics with him.
Okay.
Oh wow. Okay.
Yeah, so he would be a great fit for the quantum computing, and I think he taught something about that at one point. But anyway, Dr. Wilson, whenever we were all thinking about taking this general relativity course, we said, well, we need to have at least 6 people. Believe it or not, we had 18 people in that class.
Oh, wow!
It was the biggest general relativity class that's been taught in the state of Oklahoma.
Wow, really?
So pretty cool.
There's something interesting about being like one of those 6 students though who sign up first. So our solid state devices class with Dr. Lamachani, our advisor, right? Research advisor. Over the summer, the beginning of the summer, he's like, hey, I'm trying to put this solid state devices class together, and we need 6 people, right? And so I kind of pushed it to the side because I was like, I don't know if I'm going to be able to do 15 hours plus, run physics society, do research,
No doubt.
go to conferences,
It's a lot.
and I was trying to push physics society a little bit further, but I was like, I was the sixth person to sign up. And so, I thought, I was like, well, maybe I'll just sign up and drop it. But first day in class, he's like already got me hooked. We're talking about crystal structures and things like that. So really, I like 6 people in there because then you can just really
It feels
engage.
like you're almost having kind of more of some camaraderie. Just, hey, we're all here. We all want to know about this subject versus a class that there's 30 people in and half of them don't really care to be there. Which is, it happens. It's got to be that way. Everybody's got to take a class that they probably don't want to take. But for that general relativity class to come through and not only just have 6 of us, but for there to be 18 was absolutely unreal. And the coolest thing about it was, when we were all trying to plan this out, Dr. Wilson's looking for a textbook, and this is one of the other things I love about him, is that he wasn't trying to find the most expensive textbook or the most appraised textbook. He would find the one that's the best, for the purpose of teaching. And sometimes that would just be a free PDF online. But this general relativity class, we had a workbook, and I still have it. I think I showed it to you at one point. But it was a workbook where instead of going in and just, we got to read a chapter, do these homework problems, every day we would just come in and solve workbook problems. And he hardly even taught the class. I don't mean that in a bad way. I mean, it was a good thing because he would just kind of sit back and let us talk amongst ourselves. He'd say, okay, who wants to come up and solve this problem? And somebody would raise their hand. And I went up there a couple times. A little side note, one other thing I love about Dr. Wilson is he would put grades online so that everybody could see your grade, but he'd submit a secret name. And so he'd show you could go to his website, log in, and you could see everybody's grades in the class. So you knew where you stood. And I'm pretty competitive, maybe quietly competitive. But there was a kid in our class named Austin Dowdy. And funny enough, he actually came across centralities in my email the other day. So he's kind of on the top of my head because I was going to reach out to him and talk to him a long time. He was our class marshal. So the class marshal of our class. So super, super smart kid. He and I were in this class together, and we were neck and neck for first place. And I was first place the whole semester. He was basically right behind me, and he beat me on the final. So I still won't let that slide because that was my favorite class I'd ever taken, and I was top the whole time.
Do you remember your grade?
It was like a 97.
Oh, wow.
I think he had a 98.
Oh,
I'm pretty sure if I go look, there's a screenshot I've saved somewhere because I was a little bitter. But we were really good friends, and I'm sure if I reach out, I think he's in California doing his doctorate. I don't know in what, but so general relativity is when all the gravity stuff started to come together. Because Dr. Wilson, if you know about him, you've heard, I think, one of his talks. He is not an orthodox thinker by any means, right? He loves to question things. He, I think, espouses dissent, right? It's like if you question the status quo, I think you can find a lot more out than if you just believe it. And so during general relativity, he made a claim that I always found very intriguing. You know Maxwell's equations.
Yes.
I'm sure that kind of govern the interaction between electricity and magnetism. Well, you could, as Dr. Wilson said, you could model electromagnetism the same way you model space-time curvature. And just basically orient it in such a way that instead of it being, gravity being this kind of curve in the fabric that pulls things together, it's actually a curve in the electromagnetic fabric that charges are attracted. And his point was not necessarily that you would want to do this, but just that, maybe I'm misspeaking about his point, but what it said to me was that this model is simply a model. It's not the reality that we live in. So space-time describes the interaction of mass and gravity really well, but it's still not perfect. It has problems.
Yes.
And when he presented this kind of alternative theory that, why wouldn't you just model electromagnetism as a space-time curvature? And the attraction of of opposite charges would be due to this quote unquote curvature. And you could do it. It's just why? We already have Maxwell's equations.
Yeah.
and so what that led me into is, why don't we have Maxwell's equations for gravity? And so Dr. Wilson and I were in his office talking, and he said, well, there are such things. And this was done originally by Oliver Heaviside.
Okay.
Oh yeah.
And so you may have heard of Oliver Heaviside's step function. I think that's where most people know of Heaviside. But a lot of people don't realize that
I'm sorry. Can you?
Yeah.
Do you mind explaining that just a little bit?
Explaining what particularly?
The
kind of Maxwell and the Heaviside stuff?
The Heaviside function?
Mm-hmm. Yeah, the step function. Yeah. So the step function, if I remember correctly, the step function is basically this unit step function. So if I were to look at, say, the transient state response to a steady state response of any system, there's usually kind of an impulse response, the thing that kind of pushes or perturbs the system from its equilibrium or steady state into some new condition or new state. And so if I'd imagine I've got a car, I'm driving, and I hit a curb, right? That curb introduces a bump. That bump would be kind of like my unit step.
A step, I got you.
And so the response of this, the suspension system isn't going to be immediate. It's going to lag. And so that lag effect of, okay, you have the impulse response, the sudden spike, you can think about it kind of like a delta function, right? This infinitely tall thing with no width. And then as soon as that spike, that impulse hits the system, it creates a change in its equilibrium. And so with, say, the curb example, you hit the curb with your car, the suspension wobbles, and then it steadies out after some time. Yeah. And so the step function, as far as I understand, is just a way to kind of model perturbing a system by this unitary step, which is similar in a way to a Dirac delta function. But Heaviside, I mean, he did a lot.
Delta function is like an impulse. It's
exactly. It's the steep peak with basically no width. But of course, if I were to try to draw it, I couldn't draw it with no width. Yeah. So we have to give it this kind of
which you'll learn in Signals and Systems.
Signals and Systems. Yes, exactly. Yeah.
Signals, if you make it.
Well, Signals. That was one of my favorite classes at the time, and I took that over the summer. And of course, we used the Heaviside step function all the time. And I thought, whatever. It's just the step function. But Heaviside did way more than just the step function. I mean, Heaviside invented vector notation, as far as I understand, because he took what were once 20 equations, Maxwell's former 20 equations of electromagnetism, and reduced them to 4 using his notation.
The well-known today, the 4 equations from Heaviside.
Those are, as I think other people would coin them this way too, but in my thesis I try to be very clear. These are the Heaviside or Maxwell Heaviside equations, because Maxwell published them, right? Those 4. I'm sorry, I think he published 20, and then at some point Heaviside published those 4, and so we just called them Maxwell's equations because that's who found them. But Heaviside kind of reconfigured them into a smaller vector space, and those are the 4 that we all come to your mind, right?
Yeah.
And that's not all he did. He actually, I believe, and I'm probably misremembering a little bit, he corrected, I don't remember if it was Faraday's law or Lenz's law, but he added a correction factor, and he was the one who discovered inductance. So when they were, he used kind of a side story, Heaviside was, I think from the 8 years old, he was blind and partially deaf. And he worked as not a telegrapher, but he would, take the little telephone things and like move them back and forth, right? He's a telephone operator. Or telegraph, not telegraph, but some kind of communications thing. And so in this time around 1800s, late 1800s, 1860s, 70s, they're trying to transmit information over long distances. And they had these cables that would run under the ocean. I think there was one from the English Channel or something like that.
They call it like the transatlantic something?
Yeah, and what's interesting, and I can't remember exactly the person's name, but Heaviside was contacted by one of these esteemed communications specialists. And Heaviside solved the problem of, as you try to transmit information over a long wire, that information falls off. And so he had some, and I don't know exactly what, so I'm probably speaking out of turn, but he basically figured out what inductance is and how to minimize losses over long distances with inductors, and this whole idea of inductance. So when you think of conductance, impedance, any of those things that have those kind of like conductance, impedance, resistance, man, there's so many other ones.
He sort of like creates a repeater for like a long distance.
It's the repeater. That's exactly what it was.
Wow. That's
and awesome. I'm pretty sure that was all over Heaviside. But when I'm taking this class, general relativity, we're talking about gravity, and Maxwell's equations get brought up. And so I'm talking to Dr. Wilson in his office, and we're talking about this analogy that Heaviside presented long before Einstein had ever mentioned gravitational waves, Heaviside predicted them using wave equations. If you don't, the history of waves starts with Robert Hooke, as far as I understand, right? The kind of study of wave theory started with Robert Hooke. There was some back and forth between Robert Hooke and Isaac Newton because Isaac Newton really liked this particle or ray theory of light, the corpuscular theory of light. But Newton was a young, 17-year-old kid, and Robert Hooke was kind of an older guy. So there was, oh, well, you're just a young kid, you don't know what you're doing. And, oh, you're just an old guy, you keep doing things the way you've been doing. So there was this kind of head-butting of the wave and the particle theory way back in, 17 some odd or other, with Robert Hooke and Newton. So Heaviside, having studied Robert Hooke and kind of these like matter waves, proposed that, well, if I can describe electromagnetism or the wave of light as with Maxwell's equations, why couldn't I describe gravity with a wave? And he was the first one to do that. So those the Maxwell Heaviside equations can be retrofit into a gravitational analog, and that was when I think in general relativity, right, I just about to graduate. That's when I thought, okay, I got to go to grad school because I don't know enough. I was like, man, this is 120 years ago, and for me, it's like, well, why did we abandon that theory? Right? It's like, and I mentioned space-time. Well, if I can model electromagnetism with space-time, well, to me, it points to it being more of a model than a law. It's not a law. It's a model. At best, it's a theory.
Sorry to interject here, but I just think it's really interesting. You say, like, you don't know enough, right? And you want to go on and get your master's, right? But so many people stop at their bachelor's, right? And so, like, how do I want to say it? I don't know. I'm sort of the same way. I feel like if I were to have 2 more years getting my master's, I'll be a beast. I'll be more competitive in the market. I understand, especially for kids coming straight out of high school, and then they do four more years, or really 5, possibly 6 years if you're going to be an engineer, right? You want to get the heck out of there, right? But at the same time, everyone's talking about how competitive the job market is nowadays.
Right.
And if you want, to make sure you're going to get a job, and there's ways to get your master's paid for, right?
Absolutely.
And get paid to do research and things like that while you're, maybe that's not
what
your,
I did.
Maybe that's not your thing, but at the same time, like, you got to think about your future. And so I just think that's an interesting thing of, like, I don't know enough. Whereas for me, it's not necessarily that I don't know enough, but I want to be more of a beast.
An asset.
Right? Yeah, exactly. But also at the same time, just like, I don't really know enough to feel like I can go and do and be a part of something I want to be a part of.
I think a lot of it for me, just to be totally honest and transparent, was some fear, right? Some kind of imposter syndrome. But if I get a bachelor's degree, I go to the job, I could probably figure it out. But I would feel like I maybe I didn't have the confidence in myself of what I knew that I know that I didn't know stuff. And then went to grad school. I think the actually enlightening part of it was that when I graduated undergrad, I was like, I know I don't know stuff. When I graduated graduate school, I knew I didn't know stuff. It was like, I know I don't know, and I'm okay with that.
It's so crazy, though, because we learned so much in those 4, especially engineers. Engineer, we learned so much, right?
3,000 years of physics in a couple semesters.
And everything. But it's so crazy, though, because you still sort of feel like that you could...
There's so much more.
There's so much more.
Yeah.
Well, you close one door and 2 doors open.
Yeah. But I just want to ask, is that what your thesis is about? Like the gravity with...
Correct.
Gravitomagnetism, is that what you call it?
It's specifically GEM, gravitomagnetism.
Oh, wow.
So that term, I don't know, was... I don't think that was by Oliver Heaviside. But Oliver Heaviside in his paper in 1890 referred to the gravitic field, gravity, the gravitational field, as the gravitic field, which analogously fits nicely with the electric field. Electric meaning if I have a charge, right? Let's just say it's a positive charge. A positive chest charge is going to be repelled from that outward if you just had the arrows going away. If that charge moves, then there's a magnetic field that rotates.
That accompanies it.
That accompanies it, correct. So when Heaviside's talking about this gravitic field, what he's talking about is mass. Well, if you have two masses, they don't repel, they attract. And so there's this inherent sign change, right? That if I have two positive charges, they repel, they pop each other out. If they're opposite, they attract. Well, what makes that a little unique in gravity is that one of the assumptions that we make is that there are no negative masses, right? So that all masses are positive, thus all masses are attractive to each other. No masses are repelled from each other. So it kind of changes, I'm oversimplifying a little bit, but it's also not. It really just changes the negative sign. If you look at universal law of gravitation, G(m)(m) over r squared, it's very similar to KQQ over r squared. So if you just change the direction of that force, it's just a matter of changing the sign. But with Heaviside, right, he mentioned the gravitic field, and he called the analogy for the magnetic field, the gravitational analogy, he called it the co-gravitic field, which I didn't really like. It didn't really have a good name. So in my paper, I called it the Hevitic field, after Oliver Heaviside. So I called it the gravitic field and the Hevitic field, just to kind of give him some credit, because I don't feel like he really got much. Yeah. But what that means, by analogy, not that this is actually truth, but what the theory would imply is that there's a secondary gravitational field, which is somewhat novel, because we only know of the gravitational field. This kind of, the forces are all directed inwards, linear, right? So if I had a positive charge, all the force directions are going outward. If I had a magnetic field, I get a torsional field, a rotational field. Well, what that would mean then is that if a mass moves, it generates a rotational Hevitic or co-gravitational field. Okay, well, so what? How do we measure that? Well, that was the problem I ran into in my thesis, is because I am very much, as I like to think, an experimentalist. Like, I need to play around and test and try. Well, with this, there was really nothing I could do, because how do I measure something like that?
This is just speculation,
Sure.
because I have no background in whatever the GM you guys just talked about.
Yeah.
But like, for example, when a mass is rotating, they have frame dragging, right?
That's exactly
so
right.
would frame dragging be the
Yes.
angular equivalent?
That's exactly what it is. It's either called frame dragging or the lens-thirring effect.
Yeah.
Lens, L-E-N-S-E, and then thirring, T-H-I-R-R-I-N-G. So in my paper, kind of the last thing I mentioned was that I believe in 2016, NASA has a mission to Jupiter. That it's called the Juno mission to Jupiter, and I believe in 2016 it reached its destination and is now orbiting Jupiter, taking pictures. It's also got a magnetometer on it, and that magnetometer is supposed to be measuring this frame dragging precession. Because if you'd imagine, if I took maybe just a vat of water and I put something in it, bobbed it up and down, it would create ripples, gravitational waves. But what happens if I rotate that mass in that fluid? It creates a torsional wave, and that kind of effect, that frame, you're literally dragging that medium, right? So that would be that effect. Now the problem is, at least for me, I don't know if NASA's had this problem. We all know gravity is the weakest force. So if by analogy, right, the electric and gravitic force are analogous, we know the electric field and the electric force are much stronger than the magnetic field and force. So if by analogy, the co-gravitational or Hevitic field, the secondary gravitational field, by analogy would be even weaker than gravity. And if gravity is already immensely weak, well, where would I even measure this frame dragging effect? Well, as NASA proposed, right, the second largest object in our solar system, Jupiter, is the best candidate for finding that effect. We could send it to the sun, but good luck.
Yeah, good luck.
Yeah,
with that.
right.
I got a question. So, I don't think I've ever heard it. So, is gravity that force less than, let's say, like a nuclear force?
Yes. So the four fundamental forces: strong force is the strongest one, the one that binds nucleons together. Second one is electromagnetic force, the ones that charge and everything. Third is the weak nuclear force, the one that causes nuclear decay or particle decay.
Right.
And then the fourth one is gravity, the
Yeah.
weakest one.
Yeah.
Okay.
That's weird. You think weak would be the weakest one?
Yeah. No, that threw me off. But
Yeah,
that's
yeah.
also like a famous problem in theoretical physics, which is the hierarchy problem, which asks like, why are the forces like arranged in such an order, but with such a big gap between the weak force and the gravitational?
Almost on the
force?
order of like 10 to the 8.
Yes,
Yeah.
yes, like a very huge
So
gap.
when I'm talking about the difference between gravity, which we all live and interact with, but it's very weak, because if I were to take a packaging peanut out of a box, right, that electrostatic force is way stronger. If it wasn't, then I would never have those little packing peanuts stick to my hand, right? Gravity would pull them down. So gravity is clearly the weakest. But if the co-gravitational field or force is even weaker by 10 to the, approximately by 10 to the 8th, how am I going to measure it? So that's where the question comes in, and I don't have an answer, unfortunately.
I remember there was a not paper, but and there was a research done which saw like there's an orbit around a neutron star, I believe. So it's like a binary system, a star orbiting a neutron star or black hole, and that black hole or neutron star is orbiting perpendicular to the orbit of that other planet, and apparently the frame dragging is so much that the orbit of the other planet or that other star is actually changing too.
Changing with it.
Changing with it.
That's wild.
Yeah,
I don't know.
yeah.
I haven't heard about that.
Yeah.
Yeah, this frame dragging effect, it's good that you mentioned that, because that's exactly what it is. It's just, we throw this fancy lens throwing effect around there. But the idea is that this Juno mission should have the capability with the magnetometer to detect it. Whether it's sensitive enough to do so, I'm not sure. I've looked into it, but I haven't really seen anything, like, oh, this is obvious proof. But for me, I think maybe what's more interesting is like, okay, well, if I could make a model of electromagnetism like space-time, well, it's not to say that space-time is wrong, and it's not what I'm trying to imply. It's just that it's another model. So why couldn't I, that was my thesis, kind of the null hypothesis, why couldn't I represent gravity as a Maxwell Heaviside statement? It's just fields.
Yeah.
I don't really need space-time. I can use it. It's logically sound, but it's sufficient, but is it necessary? Right? I think that was my challenge. And I mean, not that I was challenging Einstein, but the idea, I think that was one of the things that I did kind of go back and forth with in my thesis. If you read it, I was trying to be very careful, like kind of walking on eggshells, being like, I'm not refuting Einstein. I'm just saying that there is
that could be a
different perspective,
better model, right?
And perhaps, and that might even be mine as the better one.
Yeah.
But I think what I'm in my paper, it's like, well, if we go back to the 1890s, what other ideas do we leave at the wayside because we have a new, better one now? And then you fall into confirmation bias of, okay, and not to say this is not true, but we found they measured the oh my gosh, what's it called? Gravitational lensing.
Yeah.
Right. Sir Arthur Eddington, right, was the first one to observe the bending of light
around the solar eclipse.
Correct. As far as I know, that's the evidential proof. But I have talked to Dr. Wilson a couple times, and there's some controversy about whether those observations are accurate.
Well, then, so I've heard that they're trying to use this property to build like a huge telescope.
Yes, a cosmic scale telescope.
Yeah, you can basically peer around something that's,
Yeah,
and I believe that effect is true. But what's interesting, if you think about the space-time curvature model, is, well, if space-time tells mass how to move and mass tells how space-time how to curve, well, what does a photon do? And why does a photon bend through space-time if it doesn't have mass?
Yeah.
So there's there's a whole, like, basically if you treat the
E equals mc squared.
Yeah, but then you have the relativistic mass versus the gravitational mass, and if you ignore one of them, then C can be, the photon has no mass and moves at the speed of light. But Dr. Wilson gave a talk last year about how you could determine the mass of a photon and treat it as a gravitational mass.
Was that last semester or the...
I think it might have been last year.
Okay.
Yeah, because from what I know is that they describe photon, at least the path of a photon or any light speed particle, is as part of a geodesic, like the straight line path, the shortest path in a curved space-time.
Correct.
Yeah, so I mean...
And so it abides by the curvature, but it's not necessarily, this is because it's sufficient, but it isn't, to me, necessary that light doesn't have mass. Because if it has mass, then it would respond to the curvature. But if it doesn't have mass, we have to have this kind of rule that, well, it follows a geodesic, there's a geodesic on space-time.
So you think there's something more to it?
Right. And I remember when you all talked about the
pilot wave theory?
Pilot wave theory and the Copenhagen interpretation of quantum mechanics, right?
Yeah.
I wrote a paper when I was in quantum mechanics that I just don't think that we have it all yet, and I almost think of myself as a classicalist because I don't really tamper in quantum mechanics at all. So my thesis really was a classical theory. And to kind of bounce on that idea real quick, Richard Feynman was kind of the one who said, well, it's not fields anymore. It's just these interactions of elementary particles, quantum electrodynamics, Feynman diagrams and things like that. So I'm a little bit more of the mind that I think everything is a force, a field, and a source. And I have this kind of obnoxious little riddle. And it came to me when I was working on my thesis, and I was like, this can't be real, but it makes sense, and I'll take it. So if I take a source, right? The word source, S-O-U-R-S-E. Think about that word source.
C-E.
C, did I say
S-E?
Yeah. So spelling it correctly, right? You have a source. We put that source in a field.
You get a force.
You get a force. And I was like, that's too good, right? So you literally multiply the word source by field, you get a force. Well, the same thing is true. F equals QE and F equals MA. So if I take a force and I multiply, a force is equivalent to a source multiplied by a field. And I get a force. And I was like, that's just stupid, but it's too good to be true.
Fun word.
I mean, I woke up in the middle of the night. I was like, that's wild. So I wrote it down. And so I kind of view the universe as fields and sources. And there's kind of a rule that a source cannot interact with its own field. So you just have all these sources interacting with other fields produced by other sources, and that's how you could describe the universe.
I mean, I really agree to your idea that everything's just a model, right? Even in the presentation of the pilot wave theory, I talked about how E.P. George Box, that's a quote, right? British statistician, he says that, all models are wrong, but some models are useful.
Yeah, useful and better than others. Right.
So I really agree to that. I feel like every model we have so far, regardless if it's quantum mechanics or relativity, it's just a best model from the last one, which is like, for example, Isaac Newton's law of gravity, right? And then now we have Einstein's theory of relativity. There must be something newer and better that is more compatible with other models,
Yeah. Well, and I also think one thing too about the models, right, being how do you decide if a model is better? Is it more descriptive in its power, perhaps?
Predictive power, yeah.
But I also think it's how you minimize the number of axioms that are required.
Occam's razor type thing?
In a way, because it isn't always, I think it's somewhat of a trope that if it's the simplest answer, it's the one that must be true. There's a quote by Einstein to kind of give him, because I've been maybe dogging on that idea a little bit, but Einstein said, simplify things as much as possible, but not further. And so this idea
Don't oversimplify.
Oversimplifying is a double-edged sword. Or if I try to simplify it too much, then I lose the meaning of what it really was. And so that's, I think, maybe what led me in my thesis. I thought, well, in 1890, when they had this wave theory of gravity, why did we abandon that? Well, because in 1913, general relativity, or special relativity, 1915 was general relativity. I'm a heavy proponent of special relativity. I'm not so much a proponent of general relativity. I loved the class, don't get me wrong. But again, I think it's a
very incomplete theory.
Incomplete, but incredibly descriptive. Just like quantum. I mean, quantum, as far as I know, is the most accurate and descriptive theory we have. It can make the most correct predictions. But I would say that science isn't about making predictions. It's about describing behaviors. So if I can say, I'm going to take this ball and throw it at this angle, it's going to go over there in this much time. Yeah, because I have a very powerful model. But sometimes I feel like it's almost a trap to want to try to make predictions off of things. You may have heard you're okay to interpolate between data sets, but extrapolation is dangerous. So I'm all about interpolating between kind of known boundary conditions. But if I say, I have this set of data between this set of data, and I could just extrapolate and it should always be true, well, I know we know this in science, that a lot of things are linear for a certain amount of time, and then all of a sudden they turn nonlinear. And so you have this whole with quantum gravity or whatever, the singularity. The quantum gravity is supposed to resolve the singularity that general relativity can't describe. So there's these kind of fundamental limits.
Of like exact solutions, right?
Correct. Yeah, closed form analytical solutions as opposed to numerical solutions. Those are hard to find. So there are a lot of really powerful numerical solutions out there. But I think for me, in the thesis, it was like, well, I don't really need all of this Riemannian geometry. I don't really need all this Einstein vector notation.
Which is a pain.
It's a pain. And I actually loved learning like the Levi-Civita symbol, all that cool stuff. Because it's really powerful in its description, but I feel like there's a lot of legwork that's required that isn't necessary.
There's some really good
and I
YouTube
might be
videos.
wrong. Oh, I bet. Yeah, I remember in the class when Dr. Wilson told us, he was talking about how long it took Einstein. If I remember this correctly, it took Riemann like eight months to teach Einstein the Riemannian geometry. So without Riemann, right?
That's more than a semester.
Well, and I can imagine those conversations are pretty high level. So, but yeah, I just remember thinking, I mean, it's a very powerful description, very powerful model. But do we need all of these premises to describe the universe? I don't think so. Not that my thesis is the right one, and it's actually wrong. I can tell you why in a little bit. Because my thesis only requires 4 premises. And they're the same, roughly 4 premises you need to get to Maxwell's equations. If I remember Maxwell's equations well enough right now, I know they basically describe the source and the rotation of both fields. So the divergence equations and the curl equations describe where the field comes from, right? Whether the electric field comes from the charge. Well, there's no magnetic charge. There's this magnetic dipole. We don't have a magnetic monopole as far as we know. So you basically work off these 4 assumptions. And if I remember right, the divergence equation for the gravitic field basically comes from Gauss's law for Newtonian gravity. So it all kind of works on the same premise, but it requires less. It only requires 4 things. And everything else can be derived out of those 4 equations, which is pretty powerful. So the kind of end goal of the thesis was to take my classical electromagnetic radiation textbook and rewrite it for gravity. So I took the last 7 to 9 chapters on electromagnetic radiation. I'm trying to think of some of the names that might stand out. Oh my gosh, what is that? It's the symbol S, but I couldn't tell you what it is right now, which it's been a while since I looked at it.
Sigma?
No, it's the pointing vector, P-O-Y-N-T.
Pointing vector.
Yeah, the pointing vector. So I would derive the pointing vectors, right? See the change in the sign. I've derived the field energies and anything like that. So it all works, at least in kind of the model, but it's a little bit incompatible with quantum mechanics as far as I understand, because gravity, as far as it's described in general relativity, is a spin 2. Whereas in my theory, or really it's Heaviside's theory that I just kind of piggybacked on, Heaviside took it and wrote it up to the fields and the waves and the scalar potentials and the vector potentials. So phi, the scalar potential, and A, the vector potential. I don't believe Heaviside took it any further to describe radiation. Where does that energy go? Remember earlier I mentioned that there was this change in sign. If I have 2 charges that they're positive, they repel, and if I have 2 masses that are the same, like masses, they attract. Well, that change in sign is followed through with the pointing vector. The pointing vector tells you which direction the energy is going to go in. So in electromagnetism, the energy is positive. So what that means is if I were to take a orbiting electron, right, it would emit radiation as a form of light. Or I say electron, it'd be a photon for light, but based on the interaction, I'm more of a field sources kind of guy. I'm not too good on all little quantum particles. But there's this interaction, right, where at some point there's energy that's being emitted, and we see that as radiation, and we can measure that. And you can even see that as that energy is emitted, that loss of energy causes them to spiral inward. And we can observe this. Well, what does that mean in reverse for gravity? Well, that would mean then 2 masses orbiting each other would gain energy rather than emit it. Weird. So, okay, I've got this thing, it's emitting light, spiraling inward, energy is being lost. If I've got 2 masses orbiting each other, somehow they're gaining energy?
While they're orbiting each other.
Yeah, it seems counterintuitive. Well, in fact, this is the very reason why Maxwell decided to abandon that theory. Because he said, well, the pointing vector can't be negative, because then it means energy is coming out of the vacuum into this system, and that doesn't make any sense. Well, I wasn't really bothered by that, because I'm like, well, kind of what I think about when I think about a black hole.
Yeah.
Right? There's just energy coming in to the system.
I mean, even if you think about dropping an object, the object gains energy as it falls.
Right. From the potential.
From the potential.
Right. And where's that potential come from?
From field.
Well, I'm glad you brought up potential, because Heaviside in his paper, and I wrote this because it bothered me. Heaviside had the question of what's the difference between, and I'll ask you this, we can have a little talk. What's the difference, because I've been talking a bunch. What's the difference between potential energy and kinetic energy?
One is stored and one's actually in the particles that's like, it's added on into the system.
Close.
Well, technically a total energy system. Yeah, it's still in the system.
Right.
Yeah, you're right.
Do you have any thoughts?
It's
kind of a trick question.
I feel like one is global, one is local. So like, for example, one is in the global field.
Sure, potential.
The potential. And then when the object starts to gain kinetic energy, it localizes into...
That's a good way to think about it. And I don't know that at the time those terminologies were available to Heaviside. But his answer bothered me. So in his paper I'm reading and I'm highlighting, and trying to understand what he's thinking. And he asked himself, he says, what's the difference between potential energy and kinetic energy? And you want to know what his answer was?
What?
He said, kinetic energy is energy that's not known to be, potential energy is energy that's not known to be kinetic. And I was like, my God, dude, that's like, that tells me nothing.
Yeah.
So, but what it points at is this kind of mystery behind potential energy. And so with Maxwell and Heaviside, their question or their kind of qualm with this negative pointing vector is like, well, energy can leave the system, but how is energy just coming out of nothing? Right? But I think really the point is that potential energy is just the vacuum energy. It's just always there. It depends on where you are in your configuration space. So if you think about the statement of potential energy.
Vacuum energy?
Well, just like, Tesla says that he can,
ether
you can pull energy out of the ether. Okay. And I believe in the ether. I'm fully an advocate of the ether theory.
I mean, I've heard it's not necessarily been disproven.
Well, the whole Michelson-Morley thing didn't go so well.
Yeah.
But we just call it a vacuum, but the vacuum has properties. It's got magnetic properties, it's got permissibility, permeativity. So it's not just this like nothingness that spans between mass.
For example, like the Casimir effect.
I mean, to me, it's totally counterintuitive that you can have some space in space, right, where there's literally nothing in there. Like to me, it's just
it's a little bothersome.
Doesn't make sense to me at all how you could have that.
Yeah, so
absolute vacuum thing.
Yeah, but this kind of trying to distinguish between potential energy, kinetic energy was interesting for me at the time, because I thought, well, I never asked this question. I was like, well, potential energy is mgh, or you could think about it as kind of a classical mechanics perspective, but it all depends on your configuration. Where are you in space? So if I raise a ball up to some height, it depends on its height. Potential energy always cares and only cares about where something is. It doesn't care how it's moving. Kinetic energy cares about how something is moving. So I like that you mentioned that. I never thought about that, right? Maybe that their potential is kind of more of a global variable, where kinetic energy is kind of a local motion with respect to some type of frame.
I mean, if you think about it this way, at least that's one paper I'm working on with Levi, which we're trying to derive, it's a bit ambitious, but we're trying to derive quantum gravity from pilot wave theory.
Right.
Basically, the interesting thing about Aharonov-Bohm effect, if you guys heard about that, Aharonov-Bohm effect basically says that if you take a solenoid, right, and when you run a current through it, you have a real magnetic field in it. But on the outside, you don't have an actual field, only the potential. So what they did is the question that Aharonov and Bohm ask is the potential a real thing, or is it just a mathematical quirk? So they fired an electron around the solenoid at a negligible distance, so like at that distance there should not be any magnetic field, but they found a phase shift in the interference pattern of the electron. So they've realized that the potential, even though it's there in the equations, and in classical physics we are not supposed to think of it as real, but it actually has real influence in the electron's wave function, but it does not actually add energy to the electron the way a magnetic field would.
That's interesting, and I don't know enough about that. I have been trying to give myself some primer. I've got 2 videos on pilot wave theory.
That's awesome.
You guys are trying to talk on that nice. But I watched the video just the other night, and since we're talking about potential and kinetic energy, this is, I think, relevant. There's a famous video of Feynman. I know I showed this to you about asking why magnets work.
Yeah.
Oh, yeah.
Right? Yeah. Feynman can do his best to describe how, but answering why is almost impossible. But I watched a video of like, why do magnets work? Because I wanted to, like, okay, how I can kind of understand what they do, but why? Mm-hmm. And this guy goes down this rabbit hole. It's really good. I'll have to find it and send it to you guys. But he's talking about if I were to take two magnets together, and I'll skip all the quantum, spin up, blah, 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 orientation of magnets, ferromagnet, whatever. Take your north-south pole. If I try to slam two magnets together, what I'm really doing is I'm looking at the interaction between their quantum potentials. And as I push them together, I have to have enough energy to overcome that quantum potential.
The Coulomb barrier.
Yeah. And I can do that with weak magnets. But if I get really strong magnets, I mean, I'm not going to be able to do it without a machine.
Yeah.
And the opposite's true if I put their opposing poles together, where there's a potential well as opposed to a potential hill.
Yeah.
So if I slam two magnets together, I'm trying to push them up their potential hill. Whereas if I let two magnets attract, they're just falling down a well. And I was like, that makes so much sense. Because what it is, and back to the spin thing, it has to do with how the spins are aligned. If I've got two spins pointing this way, they oppose each other because they want to reorient. So that spin is like, oh, I'm going to push against you because it requires so much more energy to bring you together because they want to re-separate themselves. But if I flip them, then they're like, oh, we come together with no problem.
Which is why quantum tunneling to me is so
crazy.
When
you talk about solid state, that was where I was like, man, because I know I took analog, we talked about NPN, PNP, and I was like, whatever, doping, I guess. That's dope. But I didn't understand what the whole quantum bit was until I took solid state with Teo. And I was like, this is cool. Because we talked about LEDs, how LEDs work. You have, certain voltages give you certain lights depending on what I'm trying to remember. It's been a long time, but all that stuff is so cool, and how they finally figured out how to get blue light in LEDs. I mean, that was a whole challenge. So
so you were just talking just a second ago, like you've got some time put away. Like, so are you going to try to further your research? You're going to try to do something else? Are you going to continue doing research?
Are you going to get doctored? Like
I don't know.
PhD?
It's been a back and forth conversation in my head. I've had Dr. Wilson, for example, or James Chancellor be like, you're young, you should go to school.
So first, what would be your reason not to get it?
Not to?
Yeah.
Is it going to change my quality of life?
Yeah.
That's really the question.
Valid.
Yeah. Like if I were to go to school for 4 more years, because I'm out of school, so I wouldn't be able to do a continued program. I'd have to start over. I wouldn't. If you asked me a year ago,
can you say that again? So if you go out of, like, for instance, if I get my master's, right, kind of like what you did, right, and then go and do some things in industry or whatever, and then come back, I can't just.
Well, I might be misspeaking a little bit but from what I remember, if you continue your track, like I can go from undergrad to master school to postgrad in a continuous sequence. But if I stop and come back, I kind of have to recalibrate, retake some classes because I'm going to be in a different program, and we don't offer a PhD here at UCO, so I'm going to have to start over in some regard. Not yet. Exactly. But it's not that I wouldn't want to get a PhD, and not that I think, oh, you don't need one. But I think as of right now, I get more out of just asking questions. I miss going to class. I just don't miss taking exams.
Yeah.
So I find it like, as long as I still have the motivation to want to learn on my own, I'm going to do that. And I think the other thing is you got to have people you can ask questions for. There's a reason why you have instructors and professors because they've studied this stuff before. So like when I was doing my general relativity course, I knew nothing about gravity. I knew general relativity was super cool. And then he hit me with this crazy, like almost like unorthodox, just totally pulled this is the way it is over my, you can think about it this way, but that's not the way it is.
Yeah. I don't like the idea of like, convention is the way to go,
Yes.
Yes.
Always.
I mean, consensus is important, scientific consensus when it comes to proof or evidence, sure. But I feel like just because it's what we accept now doesn't mean it's true in the future. Right. The same way Newton used
Well, I mean, we could say that about the Ptolemaic model of the universe, right? Or even what was it, the epicycles, right? You could take all these concentric epicycles and then actually get a very accurate representation of the universe. But until Johannes Kepler comes around and says, yo, it's just, they're just ellipses. They're not like all these weird... it's like these circles embedded in circles, which if I remember right, that's the same thing as what a Fourier series can do.
Yes.
Right? So you're basically taking these I could have n is 20 and I'd have a very good approximation. I could
You're looking at the oscillations.
Right. So, I just think that it's always good to question where something comes from, because you'll learn a lot more doing that than you will just taking something at face value.
Go ahead.
So after you got your bachelor's, did you feel that you had the tools to be able to learn on your own, or did you feel that way after your master's? When did you feel that?
That's a good question.
Because my whole thing is, I feel the same way too. Like, why would I need to further my education if I feel like I have all the tools, like, to be able to learn on my own?
Yeah, no, that's a good question. And I've talked to Dr. Wilson about this before too, because, before even with the AI stuff, we would have conversations about this idea of the legacy systems, that college is kind of a legacy system of like, you go to school for 4 years, you get a degree, and now you can do a lot of this stuff online. I can go watch YouTube videos, and to be totally honest, you can probably get a lot more out of some of those YouTube videos than you can get out of a lecture, because you can pause it, you can go back, you can, you know what I mean? They present it with a kind of a visual aid. 3 Blue 1 Brown, I absolutely love his videos, right? I've learned probably more from some of those videos than I ever did in some of the other classes that I was supposed to learn that stuff in. And also at the same time, it's probably worth saying that had I not seen it before in another class, it wouldn't have made so much sense the second time. But I think this idea of, I've got to go to school, I got to get a degree, it's somewhat antiquated. I think, this is true just not necessarily with physics or STEM, but I mean, not everybody's supposed to go to college. Heaviside was an autodidact. He learned everything himself. He didn't go to school. And so it's not like, oh, you don't need a PhD or you do. I just think some people have different
learning methods. Yeah.
Different learning methods.
Yeah, and also I think there's a thing of like, if you want to, especially if you want to be a professor, right? You definitely want to go down that road, right?
Right.
Of getting the 4 or 6-year degree, possibly doctorate, right? But so because in entrepreneurship, the sort of the philosophy or the saying goes like 4 years of school is overrated, 2 years is underrated. And
interesting.
Yeah, and so like you said though, I think it depends on what you're driven to do.
Yeah, what do you want to go? What do you want out of it?
Yeah.
I think people have said, "Yo, go back to school, go get a PhD." If you would have asked me this a year ago, I'd be like, "Yeah, well, I'm not sure still, but." If I would do my thesis I would just continue my thesis into a dissertation. I'm not as naive anymore because I've realized after doing some research, and some of my students have asked me questions about that thesis. And so after kind of following up, doing some if I was going to go to PhD school at the time, a year ago, I would have said, I want to take my general GEM, the gravitoelectromagnetism, and turn it into some kind of quantum gravity. Well, they're incompatible. Because one of them is a spin 2, one of them is a spin 1. And what that really means is that basically you get quadrupole radiation in spin 2, but dipole radiation in spin 1. So my...
Tensor waves.
Exactly. So I'm only looking at vectors. I'm not using tensors like they would in general relativity. As far as they've observed, gravitational waves, gravitational radiation are quadrupole and tensor.
Meaning they're pulling in all directions, right? Is that
well, more like, for example, instead of either one way or the other, is squish or stretch.
Yeah, there's another dimension that gets pulled on.
Okay.
So like when I did all my work, kind of rehashing what Heaviside did, and then building that into this textbook, it's called Marion, and I can't remember the author. It's been a long time. It's a yellow book, Classical Electromagnetic Radiation, held in Marion, H-E-A-L-D, and Marion, M-A-R-I-O-N. Held in Marion was the name of the textbook. So when they would produce in their textbook these radiation graphs, plots, right? If I were to take some electron and speed it up to relativistic speed, you get this kind of the radiation goes forward. It propagates outward based on the positive pointing vector. Well, gravity is the opposite. So it points backwards and kind of has this like thing behind it. So I pretty much just replicated all of those for gravity, but it's a dipole radiation pattern, not a quadrupole radiation pattern. And so if measurement says, well, we're getting quadrupole radiation, then my theory's wrong.
Or could it be that you just need to expand more upon it? Because like
that could be true too. But there is something about it. I can't remember exactly what, but there is a fundamental premise that leads it to being dipolar, and you'd have to upend that whole conversation. I can't remember what it was. I'd have to look, because I thought about that. I was like, couldn't I just go back and like change this premise, or what if I just change that? But it's almost entirely incompatible.
Yeah. Because for me, the reason why I'm like team pilot wave theory is also because because we already know that quantum systems are in a lot of times, especially with entanglements, non-local, right? So in a lot of people, at least most of the conventional people would take Copenhagen. But I feel like if another reason is because pilot wave theory isn't compatible with relativity yet. There are attempts on
general relativity.
Yes.
Because it does come from special
relativity.
Correct. Right.
So it's more like the frame of reference thing.
Yeah.
But I mean, to be fair, all quantum mechanics systems are not like compatible with general relativity.
Oh yeah. So it's not a problem anyway.
Yeah. So it's but like there are already special derivations that extend to special relativity. It's just that it's incomplete. A lot of people say it's incomplete, which I agree. I mean, that's the whole point of a theory. But the problem is people abandon it too soon. No one's going forward with it.
Right.
Even though it's making the same predictions as the other model, Copenhagen model.
Yeah.
So.
Yeah, it's always interesting when it feels like something is just right on the cusp, but it's like, it's not good, I'm going to throw it. It's like you're throwing the baby out with the bathwater, right? Instead of, well, there's something good here, right? There's something worth keeping. And so for me, whether my thesis was right or wrong, I don't really care. What was interesting is thinking there's some other way I could describe these interactions without this really complicated, and I mean complicated, not just complex, because it seems to me just a little bit overcomplicated. All of this space-time curvature and, because you can't use non-Euclidean geometry, all this stuff, and it's like, well, why couldn't I just make a model that's Euclidean, planar space as fields and forces and get the same thing? Now, the difference is I'm not getting the same thing because there's quadrupole radiation and I'm getting dipole radiation. But it speaks to there being, I think, more to the story than what either of those have at their foundation.
I mean, to be fair, like mathematics is just another language.
Right.
And any language can be made into a good story. It could be self-consistent, it could be paradoxical, it could be self-conflicting. But at the end of the day, it's just another description. It's just that one is quantitative, one is qualitative. It's just both, but both are languages.
Right.
So were you like dead set on this, the direction that you went with your research, or was there some other things that were sort of like pulling at you?
Yeah. No, that's a good question. For the most part, I was pretty dead set because Dr. Wilson and I did my undergraduate senior design project under him too as a gravitational wave detector. So there was a little bit of like, oh well, I mean gravity's cool, but I didn't know crap about gravity when I was a senior, other than pull stuff down. But the idea that in our gravitational wave detector there was a guy named R.T. Cahill, an Australian guy, I think he was a teacher. He had this idea that if you take two Zener diodes, these are quantum mechanical devices, the diode, right, this kind of, they're doped with a certain whatever, current can go one way, not the other. Well, there's a quantum mechanical interaction in those diodes, and his claim was that if you put two of them in parallel and separate them by a small distance, they, when you measure their voltage across them, there's the fluctuation that is unexplainable. And his idea was that this quantum fluctuation was gravitational waves passing through the diode and interacting with them.
Yes, I just want to cut in because I actually saw a paper that's published in UCO from a UCO student that used Zener diodes to detect the tidal forces of the moon.
That was probably ours. Was it the poster in the
hallway?
Yeah, that was mine.
That was crazy.
Yeah,
I was about to say that.
And if you read this, the conclusion though, it said we don't have any evidence to prove this because it was all speculative. I thought, I'm looking at this signal, and this is crazy. I'll tell you a little story. So I had 4 research partners. They were all physics majors. They don't do that anymore. They won't let us do that. It's all gotta be, you gotta have one from each discipline. But we were lucky that we were we had 4 physics majors all on the same team. Yeah. Also a little unlucky because if you know physics people, they like to butt heads because I got my way, you like your way. Anyway, so we were doing this thing, and my buddy Tim, my partner, think he was up in Michigan or something. He went out of town for like maybe a month, maybe it was just a week or two. Anyway, he was gone for a little while, and on that poster, there was I think his was in blue, mine was in orange, but we had all of our data, and he would put his Zener diode up in Michigan. He took it with him and his little detector, and again, we did not believe this was measuring gravitational waves. We just thought it's some noise, right? It's like it's just why is it jiggling like that? Mm-hmm. But in a very like repeatable fashion. So it's like something's doing this continually, but we don't know where it's coming from. I mean, could it be the cosmic microwave background? I don't know.
Could it be like AC current from the outside?
So what we did, and that's exactly what we thought. We thought, I mean, what if it's the because we noticed during the day there would be a rise and a fall, and I thought, well, maybe this is the light or the AC in your house getting hotter and cooler. What if it's a humidity thing? What if it's a vibration thing? What if it's a radiation thing? So what we did is we tested. We put it in I took like a hair dryer and I just hit it with heat. Of course, electrical circuits respond to heat. So we saw how it would behave. So we ruled out temperature does have an effect on it. Dr. Wilson had an old microwave radiation like can thing. So we took this emitter and we shone the emitter at our system and just, emanated it with X-rays.
Is it like a microwave laser?
Microwave, not X-rays. It's weird. It looks like just a speaker box, and it's got this weird little coil on the end, and you don't want to stand in front of it. But yeah, we dosed our thing, and nothing changed. So we were like, okay, it's not a radiation. At least it's not microwave radiation. We didn't have X-rays or anything to check. We also checked humidity. So we had like a little, like kind of a fog machine that we'd stick it in, like an aquarium type situation. So obviously with humidity in circuits, it's always not the best idea. Mm-hmm. But humidity didn't have an effect on the signal, right? So we saw if it changed everything, it shifted the whole signal down or the whole signal up, just like with temperature. Mm-hmm. So it didn't affect the variation, just its kind of median. So we also checked vibration. There was a team that had a thermoacoustic refrigerator, which, cool side story, they took, thermoacoustic. So thermo, right, heat. Yeah. Well, they use sound waves and beat this little cylinder of air with sound waves to cool it off. Pretty cool. So they made an acoustic refrigerator.
What even makes you think of that, right?
Dr. Wilson.
Okay.
So they had this really cool thermoacoustic refrigerator. It was made out of like a sub-speaker box for your car.
Yeah. Wow.
And so what we did is we took our device, we just slapped it on there, and we ran it through as wide a range of frequencies as we could, and no effect. So we're like, well, it's not vibration. We thought maybe it's a truck driving by the road, because that's how if you have a quantum gravitational wave detector, it is going to be sensitive to extremely low frequencies. It needs to be. So something like a car driving by, maybe 5 hertz, right? Maybe that might get picked up. So the idea is to try to filter out everything that's over like 1 hertz. So we're talking we're talking 0.1 hertz here.
Yeah, I'm thinking how do you set up the control? How do you set up a...
Do you have one person running by,
No, well, the control is just we had one just sitting in a lab room by itself for 3 months.
Okay.
Tim took his with him to Michigan. I took one home with me. Our other teammate Cody took one with him, and then Jacob took his with him. Okay. So we had 5 of them running. And just compared the signal. So if you're over here in Michigan and you're getting the exact same signal waveform that I'm getting in Oklahoma, with a time shift though, which there would be a time shift if there's gravity moves pretty fast as far as we assume it moves at the speed of light. I don't know that it does. That was one thing I mentioned in my thesis, that it could move faster than the speed of light. Yeah. It could move 20 times slower.
And that's what's sort of counterintuitive, because it's you would think something that travels either faster or at the speed of light would be a lot stronger, right?
Yeah, if it's moving that fast, perhaps. I'm not sure. But it was just weird that there was this time delay between my signals and his. But long story short, we got this little detector, and you mentioned lunar tides. Yeah. Well, I was looking at the OSU, Oklahoma Water Research Board. They have these buoys that are in these underground wells. Yeah. They can see water levels in these not aquifer, that's the name of the stuff. Aquifers, right? Just these aquifers underground. And they have these little bobs in them, and they can read them digitally. And so what they found, and this measurement that they get, during these diurnal tides, you can see the water level it basically goes up, it goes down, it comes up a little bit, then it goes down, it goes way up, and then does this kind of double repeating pattern.
Yes.
I noticed that exact pattern in our data, and I thought, that's just too coincidental, right? Well, of course, just because it's correlated doesn't mean it's causation. But that in of itself is a little bit of a trope, just like Occam's razor. So even though I thought that's similar, the only thing I could do as an undergrad, because I had no experience with digital signal processing or matching, whatever, was just to overlay them on top of each other and say, okay, well, here's the water, here's the lunar cycle, and then here's our data. And there was a really eerily not perfect, but enough for me to think there's
some level of correlation there.
Enough for me to be like, okay, I can't make a conclusion.
Significant.
That's what we had I think MATLAB had a signal processing package, and I couldn't figure out how to get it to give me some type of confidence. So I had no way of gauging how good or bad it was correlated. But to me and to everybody in my team, and even to Dr. Wilson, it was like, there's something there. It's not just random noise. And so that was kind of our conclusion, about as far as we could take it, was that there's something happening in these little Zener diodes. And but the kind of the cool goal was thinking, oh man, if we could get all these gravitational wave detectors, we could, Zener diodes are like 10 cents a pop. I could put a gravitational wave detector in every single high school in the country for like $5. And how cool would that be to get an array, almost a global array of detectors? And you can literally see gravitational waves passing through the Earth.
That's a crazy idea.
But didn't really come to anything too meaningful in that regard.
Just in case, do you still have those data? Do you still have access to those data?
I do have the data still. Yeah.
Because what I'm curious about is someday we could all do it together.
I'm sure he has
how with ChatGPT.
I'm sure he has some amazing Excel file.
It's all in the spreadsheet.
So can we someday we can sit together and just analyze whether or not it's statistically significant.
Significant or not? Yeah. I still got.
I think that'll be pretty cool, especially if you actually manage to find out if it's statistically significant. You can update your research.
Even if it was 70%, I'd be like, that's something.
That's something, and I feel like that could be pretty big. In my opinion. That's pretty cool. That's one of my favorite things that I read in the hallway. Too. That's why I sit there.
I love the poster. I still have one at my house, but it was always a little frustrating that we didn't really get an answer. Because, and I'm sure you guys will see, if you haven't seen some of the senior design presentations already, a lot of them are like, hey, I have this product, right? I've kind of made this thing that I can put on the market. Well, we were in a weird spot because nobody's really going to make money off these little Zener diode detectors. But for us, it wasn't about a product that's marketable. It was about what can we discover? And I think that was something that was a little unique, I think, to the senior design teams. So I always found our poster to stand out a little bit. Because it wasn't so, we made this thing that Boeing's going to use. And I don't mean that in a bad way. Because, there's some cool projects that people have done where they've taken something that Boeing would spend $40,000 on and they brought it down to like $7,000, right? So there's some cool stuff that they do. But for us, it was a little challenging because there was this kind of marketability that we just didn't have. And so we had to kind of sell it a different way. And it was selling it like, oh, well, we might be able to, get all these schools to collect a mass amount of data and we could figure out if there's gravitational waves. Because this was right in the advent of when they had first detected the gravitational waves, right? And that was when that research started for us. It was like, oh, that'd be a really cool thing to do.
Yeah, because I guess it's not really, senior design is not like a research, right?
No,
you're trying to build a product, right?
That's right. For the most part.
Yeah. And so it's my first semester of senior design.
Yeah. Okay.
And I'm excited, right?
Well,
and
try not to be too worried about it being a product because I know that's
there's
the goal, but
unconscious pressure.
Well, it is, and when we. I don't think they do this anymore. We had an elevator pitch contest. Okay. So everybody would do this like, here's my 3-minute pitch on Shark Tank to try to sell my thing. Well, there was nothing that any normal person would care about for our little gravitational wave detector. Like,
exactly.
What I mean? Like, there's nothing that's like, I want one of those.
I don't think science should be about selling.
Well, to
completely
me,
agree.
Science is more interesting to me, anyways, and I'm sure to all of us. The things that could come from the science, like for instance, okay, you just brought up the 3-minute pitch, right?
Yeah.
Well, my favorite 3-minute pitch is mine talking about my research, and because it exposes people to so many different ideas, right? Material science, discovery of new materials, using machine learning, talking about sustainability in magnets, and talking about like how we need more materials to be able to, especially with NVIDIA talking about us needing this year is like the year for the robots or whatever.
Yeah.
And I'm sure every year after that there's going
to robotics for engineering now.
Yeah, exactly. And so if we want everybody to have a robot, just like everybody has a car, you're going to need more materials or else we're going to run out of them, right? Yeah. And so, I don't know if I could actually like try and sell you some like widget, right? No, I could sell you an idea, right?
So you use the word widget, which is great because when I talk to my intro to engineering students, I always reference my engineering ethics course because at some point you're going to go get a job and you're going to be working for your boss and they're going to say, as my ethics professor said, make me my widget. Mm-hmm. And I think that's where, and maybe to go back to your first question about, why introduce yourself, why did you get into physics and gravity? Because I was an ME student, mechanical engineering student, and I just didn't see myself working, not that I'm being hyperbolic, but like working in a cubicle making a widget, right? I was like, I want to be the one asking questions, trying to figure things out. And then there might be somebody that I can have, oh, hey, go build this thing and test this for me.
Which right? I love because like meeting you for the first time, I don't know, it was probably like a year and a half, 2 years ago, something like that.
Yeah, maybe 2 years.
You sort of showed me that like your curiosity can take you, anywhere you want it to. You don't have to be stuck in, and doing whatever everybody else is doing, right? You can think outside the box, and it's okay to.
Yes, it's okay to. Right.
Yeah, and I don't know where to go with that, but okay, so I was wondering, I've been reading a book called Deep Work, and so it's all about like being able to, because you seem to be like very like super productive, right? And it's always it always baffles me like this new thing that you've created or these like new ideas that you have to build these things, and you said you were like creating a course. It seemed like everybody loved the intro to engineering course that you built last semester. And so this book about deep work is about like, and so I want to know like, is this how you get so much done, right? So this deep work is like, okay, you set aside, let's say you start with like an hour, right? And you make sure that, they say, you build a ritual around it. So like if a ritual for you is like making your yerba mate, which is mine, your coffee or whatever,
little beverage,
to sort of like kickstart your brain to say, okay, we're about to go do this
routine.
This routine, yeah, exactly. And you're about to go sit down and do deep work, meaning like you're no distractions.
Yeah.
You have your phone away from you. You have all the notifications off. You're like focused on the work, whatever it is, right? For us, maybe it's like studying for some class, right? And so is that how you work, or like how is your like studying habits, or like how's your work habits, and like how do you get so much
work
done?
Ethic? Yeah,
it's a little bit of both. I have a ritual for sure, but I'll preface it by saying I'm one of those weird people that, like, you might see me on campus, right? Let's say I've got an hour in between classes. I can't do anything in that hour. I don't have enough time to sit down and
you need time
I need like an hour to sit down and figure out what I'm going to do. So what I do is I'll go to work, go to school, teach a couple classes, might have some time or space in between. I don't really get anything productive done during that time. I might be doing little things like printing off assignments or running something in between lab or cleaning up my office or doing little things, right? Having conversations with students, which is probably my favorite thing to do in between class. But when I get home for the day, like let's say Monday and Wednesday this semester, I usually do this any semester, but just for specific examples, I get done with class at 5:15. I get home 5:45. I will sit down either in my chair. I got like one of those little, it's called a rocker, but it's a fancy like
Armchair?
It's not an armchair.
It's like is it a recliner or is it like
it's like those camping chairs, you know? But it's fancy, like it's got a little like hydraulic on it. Okay. My dad got it for me for Christmas.
Okay. But wait. You're sitting in your house.
No, I'll go in the backyard.
Okay.
Okay.
I was picturing you in the house in one of these
little camping chairs.
Yeah.
No, I sit on my back porch because I've got a really nice view of my like the backyard looks over some trees. Like there's no other house in my backyard.
Beautiful.
And I'll sit out there for an hour and just think about, and I do this in a weird way. It's developed over the years. There's this method called the Eisenhower method.
Okay.
And the idea is that you always do what is necessary first and what is urgent. Then you do what's necessary but not urgent. Then you do what's urgent but not necessary, and then you do whatever's left. And so back in the day, this comes from President Eisenhower. He had 4 bins on his desk because when you get all this paperwork, you can imagine being a president, all the paper stack up. Well, he had 1 bin that's necessary and urgent. He would do all of that one first. And then he'd do his necessary but not urgent. If it was urgent but not necessary, it comes after, right? Because it needs to get done, but if it doesn't get done, it's okay, right? It's not necessary. Then whatever's left in the last bin, if there's any time to do it, that's what I do. So people probably know I'm a little bad about getting back to them on email. It's because I treat it in this method. So I'm not going to say anything. Well, I look at it, and that's not and I think I might have pissed somebody off one time when I said that email wasn't urgent.
That's why I come find you.
Yes.
I'm like, you're typically in Howe Hall.
Yeah, if you
right,
find me, stop
somewhere in Howe Hall. So I'll just go walking around.
And I'll cross through the hall. And hey, let's chat real quick. And that's so much better because if I get an email, for me, it's okay, what am I going to say? How am I going to type it? How long is it going to take? So there's this kind of extra work that's associated with it. So usually if it's an email like, hey, I'm not going to make it to class today, right? Probably not super urgent, right? But if it's like, oh, hey, I don't know, something happened. Can I make up the test tomorrow? Right? Something that's urgent I will respond to or necessary. But things that are just kind of there, not to like say they're not important.
I'm just going to start putting in the
important.
I'm just going to be urgent in the subject.
Well, I know Saul will do this. She'll send me emails with the little exclamation mark. So if I see that, I'm like, okay, we got to deal with this. But I do this with everything, whether it's email, with text message, with friends sending me memes on Instagram. Like, if it's not important and it's not necessary or urgent, I'm just not going to get to it first. If I have time over the weekend or, I don't know, Friday night when I get home from the gym and I'm just absolutely chilling, then fine. But back to your point about work, right? What I'll do is I'll kind of say, okay, maybe if I've got an hour in between, I don't have anything done. Well, that hour feels wasted, right? I feel like I didn't do anything. So when I get home, say 6 o'clock, from 6 o'clock to like 2 or 3 in the morning, I am just grinding. Like it is just there. You turn your phone off, flip it upside down. I sometimes put my phone in my desk drawer so that I don't even like see it go off, right? I flip it upside down, put it in the phone drawer, or put it in the desk drawer. Discord, turn it off. Email, turn it off. I will just focus for like 3 to 4 hours on tasks. And what I do is I have a spreadsheet that does the same thing that has, I list everything by its urgency and necessity. So I say, okay, the things that are on my top of my list, they're red. It's like, okay, this has to get done by tomorrow. Right? I've got to give a lecture tomorrow on units and significant figures.
I'm sure that Excel sheet was on that list at some time, right?
Making the list of like some Inception spreadsheet. Meta, it's funny because I call it my order of operations, which is pretty cheesy.
It's all good. We're all nerds here.
Right. But that's how I do it. So I sometimes am not as... I maybe seem more productive than I am, but at the same time, I like to think that I am really good at getting things done in good time. But way back to when I was in middle school and high school, I realized that I was always slower to come by things than most people. Some people could just kind of see it and pick it up and it makes sense. I have to kind of play with it and break it and try to figure out how I understand it. And that takes me longer than most people. And so, I might be able to like get this thing done in an hour, but I need time to twist the knobs and like figure out, is this really what I want? And I can't feel pressured to do it in an hour because sometimes there's too many decisions to be made. And I'm like, well, I could do it this way, I could do it this way, I could do it that way. Say you're solving a test and I've got a kinematic problem. It's like, oh, well, find where the ball goes. It's like, well, I could probably do this 3 different ways. but there's one of those ways that's the most efficient. Chances of me picking the most efficient way the first time are slim to none until I do them all and I realize, oh, that's the easier way to do it. So when I plan on my schedule, it's always really hard to be like, oh, well, okay, what needs to get done first? So sometimes what I end up having to do is just being like, hey, this is what I have the energy to do. And deep work, right? I don't know anything about that book, but I realize sometimes that I get deep in projects, and I will sometimes realize, oh, I've been spending. Side note: there's a pendulum that I'm working on for Intro to Engineering Lab. It's going to be PID controlled. That's my goal. But it's a meter stick swinging on a rod that has a propeller on the end, and you can press this propeller and get it to increase its amplitude. I can press it at just the right time and depreciate its amplitude. It's a really fun little project. I haven't stayed up all night in probably a decade until about maybe 2 weeks ago. Okay. It was 7:30 in the morning, and I see the sun come up, and I look at my clock, and I was like, it is 7:30 in the morning.
That's crazy.
It's like I have to go to sleep. Yeah. But I didn't. I was energized. Yeah. Like I was like I am going to lay down. I'm not tired. Yeah. But I will eventually fall.
Okay, it's recording again.
Okay.
Live again.
Back live.
But yeah, just to kind of
fresh Duracell. By the way, Duracell. You gotta go with the Duracells, man.
Yeah, the bunny.
Yeah. No. Energizer.
Oh, Energizer Bunny. Oh my gosh. Wow.
I've just
ruined that one.
I don't know. There's something. I don't know what they do at Duracell, but they're doing it right, man. Because Duracell is just my go-to battery.
Duracell doing it right.
Not sponsored. Not sponsored.
Hey, but if you want to sponsor us for our batteries, we'll take it. Yeah. But anyways, my bad.
No, I was just, I think with the whole planning thing, it's funny because I have the imposter syndrome of like, oh, I'm always busy. And then I gaslight myself to be like, oh, you're not getting anything done.
Same, dude.
Right? But it's like, I'm always doing something.
Yeah, my girlfriend, she's always laughing at me because, I'll be like, I don't know, it'll be like middle of the summer, and I've felt like I'm not getting things done, right? And she's like, what are you talking about? You've been doing research this whole, you're working literally 9 to 5 every day, basically doing research. I was like, yeah, but I'm not taking a class right now or something.
Well, it feels like you don't have anything to show for it.
Yeah, exactly. Yeah, like with the class, it's like, oh, okay, yeah, I've got these credits now. Yeah, I did the
just completing the homework assignment. You're like, okay, I've got this. I can turn it in. There's proof of work, right?
Yeah.
I think there's a big term in this whole Bitcoin, the blockchain, right? Proof of work is the thing that they use a lot.
Yeah. Oh yeah.
But no, I just think that when I was talking about that pendulum project, when I was up super late, funny story, just super short story. I'm working on this thing. I've got a MOSFET. I'm trying to program it. I just got the MOSFETs in from Amazon, and I'm like, these are super easy to use. I just got to plug it into my circuit, right? Well, I had this propeller on this pendulum, and the propeller, of course, it's just a DC motor, so I can flop its polarity and change its direction. Well, the way I installed it, I wanted it to go the other direction, so probably like 3 in the morning, I flipped the polarity of the motor, was doing my thing, got everything done. 7:30, all right, I'm gonna go to bed. It's one of those things where you almost wake up and it's kind of like a hangover. You're like, man, what did I even do? You forget that you got stuff done. Yeah. Like if you ever stay up super late at night, and you're like, you wake up and I gotta get that homework done, and you're like, oh, I already did it. But it feels good, but it's also like, oh, okay. So I woke up and I was like, oh man, I can't believe I stayed up and got all that stuff done. Now I get the MOSFETs and we're going to go plug that in and do this thing. When I'm working on the MOSFETs that morning, it's not working for like 3 hours. I'm diagnosing it. I'm running continuity tests on the MOSFETs. I had 5 of them. I ran every single one of them. It's like, well, one's working.
Electrical components are the most frustrating thing in the world.
Absolutely. And I'm sitting there because I was programming the night before, trying to get the motor to operate the way I wanted and have certain controls from the sensors. Well, the MOSFET comes in to regulate the propeller based on the power supply and then switching it off with the Arduino on and off. I had set everything up. I did it on Tinkercad. Everything was working, but on Tinkercad, but I couldn't figure it out. 3 hours into it, it's probably, I think I woke up at like 1, the next day, probably like 4 in the afternoon. I'm just like, what is happening? 3 hours go by. I've done nothing, right? I feel entirely not productive. And I look over at my power supply because I'm like, we're running continuity. I'm doing stuff that I shouldn't need. I'm like, talking to GPT like, this can't be this hard. This is stupid, right?
Yeah.
I look over my power supply and notice my polarity is still flipped.
Oh.
And I just, I'm like, all right, I'm just going to take a break.
Nervous breakdown.
So for about 30 minutes, I just walked away and went outside and sat and looked at the stars. You know? Or I guess it was in the day, so I was looking. But I'll do that sometimes. I'll just get frustrated. You think about something too hard, you gotta take a break.
Yeah, because
you gotta take a break.
It's so great because it's like it can feel like you're not getting anything done, right? 'Cause you're troubleshooting, right?
Right.
But like for instance, this over the summer, I spent basically the whole summer troubleshooting some code on a supercomputer, right?
Yeah.
And I feel like I didn't get anywhere, but at the same time, like I now know how to like run stuff on a supercomputer, and I know sort of, what you need to be able to do something like that.
Familiarity with it.
Yeah, exactly. Yeah. And so now, if I had, let's say somebody else gave me some code to run on the supercomputer, I could easily show them how to do that.
Yeah.
And so it's like sometimes you have to like sit back and think about it and like think about the things that you've learned from it, because sometimes in the moment you're just like, oh my gosh,
I wasted 3 hours.
Yeah, exactly.
Yep. When I even had that same thing, because I get this stupid thing figured out, and I was like, oh, well, I knew what I was talking about. I just was so frustrated that I wasn't paying attention. You almost kind of you're looking for your wallet, you're looking everywhere, and it's just right in front of your nose.
Yeah.
And I was like, oh. Well, that's just the way it is. And I'm not going to be mad or beat myself up about it. And so I think one thing that I did learn, because you kind of asked, was this something you figured out in undergrad school, or was it because of your thesis? I don't really think I had good study habits, not even just in middle school or high school, but in undergrad. But it wasn't until grad school. And I don't know that this is the reason, and I'm not going to say that this is why. But I remember as somebody who teaches engineering courses, right, sometimes we require things to be done on engineering paper. And it has this very nice grid and blah, blah, blah.
You do anyways.
I used to. I don't anymore.
Oh, you don't anymore?
No.
Oh, okay.
Well, I don't think it's really that big of a deal.
Okay.
Because when I went to grad school, I stopped writing notes on engineering paper, or even on lined paper, like lined college ruled paper.
What?
I wrote all of my notes on blank white paper. Sounds wild, right?
Yes.
Well, not only that, I wrote all of my notes in pen.
Mine would be like sideways. It'd be like...
Well, it'll be like, they do start to kind of trickle off down to the side. Yeah. But when I was in undergrad, I would write all my notes in pencil on lined paper. And then in grad school, and the reason for this is there was she was in grad school when I was still in undergrad, but I was an assistant for her UPS course. Her name was Madeline Cooker.
Are you saying lines are holding us back?
Yeah. Yes. But I noticed she was always writing her notes in pen and on blank paper. And I was just like, what the hell? Like, how are you doing that, right? Like, that's weird.
Yeah.
I was like, I need my line to keep my equation in there. And then, I don't know, she's like, try it. And so I think we were in Math Physics 2 together with Dr. Wilson, of all people. And I was like, okay, I'll try it. So I started writing my notes blank paper in pen, because at some point in math physics I had to turn my paper sideways because I couldn't write it on the 8.5 with 11 long. I had to write it with 11 long, 8.5 tall. So the white paper helped, because if I wrote it with lined paper I'd have to turn the line sideways. So writing it on blank white paper just gave me the freedom to write wherever I want.
Interesting. I wonder where she got that from.
I don't know. She was one of those people, very type A, like really good student. Yeah. And I was always kind of trying to figure out, well, how are you so productive? How do you get all your study habits? And I was like, I'm going to steal that. So through all of grad school, all of my notes were written in pen and on blank white paper. Because for probably the first semester I had was Math Physics 2, Mechatronics, and EM Fields 2. It was the hardest semester I'd ever taken. Dr. Wilson told us at the end of that class for EM Fields 2, he said, none of you deserve A's.
That's great.
And as I was saying, Madeline, right, she's a type A student. She got a B, and I said, shoot, if she got a B, I'm stoked with my B.
Yeah.
But anyway, so I'm kind of, we're good friends. She's a really good student, and I kind of took that idea from her. And I didn't realize it at the time. I just kind of thought I was trying to be a better student. She was a good student, so I was mimicking her. Well, having this kind of almost rule, if I have to write in pen, it forced my brain to take a couple extra seconds to think about what it was I was writing. Because if you're writing in pencil, there's a subconscious, sometimes conscious, awareness that I can make a mistake and erase it. But when you're writing with pen,
you gotta be careful.
You gotta be careful.
And deliberate.
Very deliberate. And so at first I'd be, Dr. Wilson driving notes. And if you know him, oh my gosh, he would fill up the board. And I don't think I did this in statics, but I was kind of notorious for people would come into class and the whole board would be full before I'd even start. That's how Dr. Wilson was, because there's just too much to cover.
Yeah.
So I'd be sitting there on my blank white paper, scribbling in pen, trying to get everything down, and I'd be making mistakes and then scribbling it out. Well, that mistake of me scribbling it out, not using whiteout. Madeline would use whiteout because she was extra. She'd bust out her little whiteout thing, but I would just scribble, scratch it out.
Yeah.
Well, that's like if you've ever heard of if you make a mistake, you hit yourself with a rubber band. You slap yourself with a rubber band. That was kind of me, like, ooh, don't do that. Maybe take another second before you write that next time.
Yeah.
Well, I got to the point where as I was writing my notes, I'd have weeks where I wouldn't make a single mistake in my notes.
Wow. Huh.
Because eventually your brain just adapts.
Yeah.
And that was where I think my kind of work mode mentality really switched from just, I have to be a student to I want to make sure that I'm kind of understanding how I learn.
Yeah.
And kind of freeing myself, kind of to your joke, right, from the lines. It was like, well, I'm not writing words, I'm writing equations. And sometimes those equations are pages long. And so kind of freeing myself from that, trying to think, okay, well, how am I going to be able to go back to my notes to make sure I see what I'm saying? You can write them in pencil, that's fine. But it changed my brain chemistry by writing with pen.
That's why I think it's so necessary to, like you did, you talked to people you knew, but I've watched like a bunch of YouTube videos about how other people study and what they do. And I think it's important to try a bunch of different things.
You need to try different things. Yeah.
Like my whole thing now is I am obsessed with like making sure that all my notes are written in OneNote, right? And so I use the so I write all my notes on my deal. But
notes is a good note.
No, OneNote.
Oh, is it different?
It's a Microsoft thing,
that's why.
So I have been obsessing about also the keyboard because so with this tablet, the keyboard that comes with it, you have to attach it to be able to start typing, right? But I like to write some and then also type notes at the same time, depending on what we're talking about, right? Like if
we're making a sketch of something.
Exactly.
Right.
And so I'll go back and forth from writing and typing, and that doesn't really allow me to do it very succinctly. And sometimes you need to do it really quick, right? You need to, and so
they started racing the board already, and you're like,
wait. So I was like, okay, I need a wireless keyboard, but I also need it to be small enough that I can just sort of carry around. And then now I've got like this. It's like way too thocky, so I'm like, okay, well now I need to get like, I need to get silent keys so I'm not disturbing everybody, but this has taken me like years to figure out,
I don't think it's something that anybody figures out day one, and if you do, well, you're special. But like, I think with when I was in middle school, just another little story about middle school. I did have bad study habits. My parents knew it. So they had me take this like study class.
Study etiquette type thing.
Yeah, and they had me do this. There's some name for it. It probably starts with a C if I remember. Where like you take a line and you draw it vertically on this third of the page, and then you got these things on this side. And like you separate it, and I was like, this is just, I could see where that might be something useful in certain cases, but it wasn't a general architecture that I could use for any class. But having blank white paper, I could use it for any class. It didn't matter if it was English or chemistry or science or physics or whatever. It's just white paper. I'm just sketching. And so I think it was like at first I was horrified. Like, oh my God, why are you using blank paper? There's no border. There's no grid.
Where do I start?
Where do I start?
Yeah.
It doesn't matter.
Yeah.
And that was where I was like, oh.
But see, like, so
it doesn't matter where you start.
I was a purist in the beginning. I only wrote in these like yellow notebooks. For one, because like when you write on this paper is like it's a very good quality paper, right?
Yeah.
And when you have a good quality pencil, good quality paper, it feels so good to write on, right? But then after a semester, I would have a stack of these notebooks. And then after another semester, I'd have another stack. And they just I've got this giant stack of notebooks. And I'm like, oh my God, that's so much paper.
Yeah.
And then like, it's not really organized, very well. And so I was like, okay. And then, I used to work for Avis and Budget Rental Car, and there was a Microsoft Surface in one of them. And we kept it around for months, trying to call people, trying to get somebody to come back and get their Microsoft Surface. And no one did. So my boss was just like, well, it's yours, I guess. You're in school. You probably need it anyways.
Nice.
And so that's what got me stuck on this thing, because it's just so nice. For one, you can easily, now the technology is great. Like, you can just hold it and make straight, perfect lines for your graphs. You can change the colors. You can highlight. Like, it's just so yeah. But also at the same time, I'm like, okay, yeah, but I'm using a lot of power. Try not to overthink it too much.
Yeah. Well, I mean, when I got my iPad as a teacher about a year and a half ago, that I'm almost overly organized, which sometimes it sounds like, how could that be a bad thing? But it's like, like with my spreadsheet, sometimes I'll spend more time trying to organize myself.
You've got the craziest Excel files I've ever seen in my life.
They're, I think if somebody found my hard drive, my whole life is on a spreadsheet.
That's crazy.
But Excel's super powerful, and so I think at some point it was just an easy tool. But sometimes I'll find myself spending more time trying to organize myself than just executing. Yeah. And kind of back to what I was mentioning about undergrad, right? Where I was like, I don't really want to go get a job. I don't know enough. Maybe I'm like kind of fearful of like not knowing what I should know as a physicist.
So like paralysis by analysis type thing.
Exactly. Analysis paralysis, 100%. And grad school fried that, because it was like, you don't have time to figure it out. You just, where do I start on the page? It doesn't matter. Just start. Right? Yeah. And so it kind of almost by brute force made me just do. Whereas I think I'm an experimentalist, but I find myself sitting and thinking about things a lot more than I maybe should. I should just start doing and trying and failing. Yeah. And there's a quote, and I'll try to see if I can remember exactly who said it. Maybe it was Abraham Lincoln. I'm probably wrong. But he said, if I had 3 hours to cut down a tree, I'd spend the first 2 hours sharpening my axe. And that's for me where my kind of ideology has always been, that I would rather spend 2 hours thinking about the problem and then 1 hour just doing it.
There's a balance.
But we can't always do that because that's assuming that I'm asking the right questions to begin with. Okay, I'm sharpening my axe, I got to cut down a tree. But if I'm trying to write my thesis, I don't know that I'm cutting down a tree. I'm just swinging at one. Right? I don't really know what...
figuring out what you're using.
What am I doing this for? And that's not an obvious or trivial thing.
Well, I have the same problem with like a bunch of different things. Like, I get very obsessed with things. Like, for instance, with the keyboard, right? Like, the last 2 weeks, I've been obsessing about like making sure I get the right switches. Making sure I'll be honest, this is my fourth keyboard.
No. So wait, the other one that you showed me the other day, which is what?
That one was wired. So I thought it was wireless, but it wasn't. So I took it back, and then I got another one, but I realized that it didn't even have the arrow keys on it.
You gotta have the arrow keys.
You gotta have the arrow keys, and then
you can forget the number pad, but you gotta have the arrow keys.
But what I liked about the first one is it was Hall effect keys. So it uses the Hall effect instead of
like button presses.
Actual
pad.
Exactly. It goes off of the
things passing through a sensor.
Yeah, exactly.
Wow.
And
is that not expensive?
Actually,
surprisingly not.
That board was like $46.
Really?
But now that I've learned, like, okay, well, the Hall effect keys are typically with keys that you plug in. Right? I think maybe they take more power, or there's something there that you need, I think, extra power for. And you can't just get a wireless keyboard and have Hall effect keys. I believe they do make them, but they're like 170. I wanted to spend around like $50 or whatever.
Yeah.
And
so how much was this one then?
This one was $56.
Oh, sure. Okay. Not bad.
Yeah. And it's wireless, and it also has like the USB-C. We can wire it as well. but like I would be up at night, like thinking, just in bed trying to sleep. I'm like, oh my god, I really hope those are the right switches. And then,
you don't know until you try.
Exactly.
Yeah.
And so I'm the same way with like once I go down like a new rabbit hole, like trying to find like the right textbook or the right book. And so I'll spend...
It's a hard thing to answer.
I'll spend hours like on the web searching for like the free PDFs and like trying to find, okay, well, which one's the best free PDF, right? And then I'll ask ChatGPT, and then I'll ask Claude, and then I'll ask Gemini, like, all right, these are all saying sort of the same thing. I guess we'll go with this one. And then I start reading them, like, well, this one's a little too high level, and so I need to go find another one. So definitely.
Yeah, it's because you mentioned analysis paralysis. That's exactly what it is. But I think it's maybe just a.
I feel like it's a matter of asking quality questions.
I think it is, but I think it's something that people in our field seem to just kind of inevitably fall into. Whereas it's not so. It's
like attention to
detail. It's not a bad thing that I want to ask all these questions and kind of wait before I make a decision. But there's kind of two personality types that you could argue. There's risk averse, and then there's risk prone, or willing to take risk. And I've always been one of those people that's like, I want to make sure I've calculated every option before I take a risk. And you can't always do that. And so I think it was right there after EM Fields 2 and Math Phys 2, and I started taking notes differently, that it was just like, there isn't a right way to be a student. I just have to figure out how to be my best student. Right? How do I understand things? Cool. And like, I might see Madeline doing something and she's, just clicks, right? And then I'm like, I'm spending 3 hours in Dr. Wilson's office being like, well, what do you mean by proper time? Until I figure out what it means for myself. And nobody can tell you how you understand things yourself.
It is, I don't know. It's just so fascinating. I don't want to say, there's just so many things to think about, but sometimes you just need to go for it, right?
And then where do you draw that line? I think there's not a right or wrong answer.
And just, what I've learned...
For me, it's the necessary and sufficient. Right?
What I've learned is typically, if it's something I'm like really excited about and want to do, and that I know typically, like after I do that thing, is going to be like relief, and it's going to be something that actually makes my life better. So I'm just like, okay, just whatever I think of now, I'm trying to just go ahead and go do it, right? Like we've been talking about this podcast for a while, and then whenever we got back this semester, I was like, let's just do it. Like let's just.
Not everything needs to be perfect. Because iterations are better than perfection at the first run.
Exactly.
Especially on a low budget.
Absolutely. It's funny you kind of mentioned this, like when you have something that you're like kind of really motivated or interested in, you just kind of want to focus on that and get it done, because then you can worry about other things. You're not so stressed about that one thing that's just really burned in your brain. I have this theory called the bag of chips theory.
Okay.
Ooh. So when I was living at my parents' house, my dad and my mom would open a bag of chips. Let's say they get like 3 bags of chips from the store, right? My dad would open all 3 bags, and he's like, I'm gonna need some from there. I don't know why. I really don't know why. I don't know that there's a reason for this, but I've always been like, well, I'm going to finish that bag of chips before I open the next one. That one, I have to just, like, it's sitting there open. Like, is it, it's not maybe even that I'm worried that it's going to spoil, but like, I've opened this task. I need to complete this task before I move into the next one. And so I call it my bag of chips, because like some people can open 10 bags of chips and just kind of incrementally work at all of them. I can't do that. I'm getting better, because I can be like, I'll send a couple emails and I'll go do this and spend 10 minutes on that. Like I said, if I've got an hour in between class, I really can't get anything serious done. I can only get small tasks done. And so when I get home, it's like I've got, a 5-hour project that I want to work on. Like I have to just completely zone everything else out and just and focus on that one task. I can't go nibble on over here. So this is maybe something I've even learned in the last year, that I separated my day into 2 pieces. I kind of have my nibbling in the morning, in the afternoon, and then I have my feasting in the evening, right? So I don't.
Where you actually dig into
and it ironically is true because it's the same way I eat. I don't eat breakfast, which is probably not good. I also always eat a late lunch. Like I know we talked about getting food before this. I didn't. I was just too busy. So I'll go get lunch or whatever before I go to the gym. But I'm usually kind of like wake up, do my stuff, get everything that I need to do that's necessary out of the way, and then I can focus on what I need to do for the next day. And I can't mix them together. I have to say, okay, we'll knock out random little things here and there, go to the store, go run errands, do little things, answer emails, print stuff off, small, not high stakes tasks. That if I don't get it done, I'm not dead, but if I do, knock something out that's small.
Well, I think a lot of part of my worry and stress is because I love variety. I like to have I love to have my hand in a bunch of different cookie jars, right? And so, I have.
So we have two archetypes right here.
so this I have tried to tell myself each semester, don't do more, but I end up doing more for some reason.
Right.
And, but at the same time, I think it helps sort of show myself that I can keep pushing myself just a little bit, right?
In different directions. But I also think maybe because I can relate a little bit, right? If you get too stuck on one topic, it almost kind of burns you out. Like I was working on that MOSFET for 3 hours and it's not working. I mean, I wanted to throw that thing through the window.
Yeah.
Once it works, I'm like, oh, okay, now we're chill. But sometimes if you spend too much on one thing, you're almost like, I don't want to talk about it anymore. Yeah. Like I went to my buddy's birthday. At their house, they had everybody over, the pool party and everything. And I was talking to my buddy Carlston about the lab manual I'm working on. And my buddy Austin comes up, he says, hey, so how's the lab manual coming? Because they all know I've been stressed, busy working on it. And Carlson's like, don't ask him about it. It was mostly a joke because I'm happy to talk about it. But sometimes you just dude, I don't. I want to go back just a little bit because we were talking about my thesis. For 2 weeks, go ahead.
I'm sorry, I'm trying to help you out here. I don't have anything going on for the rest of the day, but I know you do. It's 3:30, so I don't know.
Well, I just have that meeting at 4. At 4 o'clock specifically, I just need to pop my head in and say, hey. Okay. But thanks for the heads up on time. But regarding the thesis, so we're talking about this negative sign, right? If I have electromagnetism, they repel, positive, it's like masses, it's the flip of the sign. Same with the pointing vector. Well, for 2 weeks, I was going through all of the derivations for gravity and all the derivations for electromagnetism because I had lost a negative sign in one of my derivations. And I was putting it up on the board all over campus as a joke, being like, help me find my lost negative sign. And I told Dr. Wilson, and this is just total transparency, because this, right, when my idea was, okay, well, there's got to be a negative sign here. If it's not there, the whole thing's wrong, right? The theory, the thesis is just, what did I just waste 6 months on? Yeah. And I joked with Dr. Wilson, I was like, what if I just put it back in? I didn't though, right? But it was just like, man, it's just, I don't know where it went, but it's got to be in there. So for 2 weeks, I was looking for it, and I would put it all, we've got these big boards in the library. I filled up the whole board. There was a guy named Fu who was a student here, and he was really smart. I was always asking him, hey, Fu, if you got time, go through this, see if you can find it. He couldn't find it. But one day, I was talking to Dr. Wilson because I was like, man, I don't know what to do. This is crazy. And he said, well, what I want you to do is I want you to take, so you have 8.5 by 11, right? 11 long, 8.5 wide. Well, they also make a 17 by 11 page, which is 8.5 times 2, right? So just take it. It's twice as long if you flip it long ways, and it's 11 tall. So it's basically 2 8.5 by 11s right next to each other.
That makes sense.
And he said, what I want you to do is I want you to take everything from Held and Marion, the classical electromagnetism book, electromagnetic radiation book, and go step by step, side by side, line by line, equation by equation, and make sure it's the same. And for 3 days, I have 27 pages of just these duplicates. Here it is for electromagnetism, here it is for gravity. And I had redefined the curl of the vector potential, del crossed A, as a negative, just to make it easier for me to plug back in. And so that's where I had redefined it and then lost it. And I was like, oh. So for 2 weeks, I was like, oh my God, where is this at?
So there's important,
frustrating.
important to take notes of what you changed.
I had to really find it in myself just not to put that negative sign in.
Oh,
right? Because it was like that's not good science, not ethical.
For sure.
And if you've seen Star Wars, Empire Strikes Back, there's the scene when it starts with a Z. I can't remember the character's name. Nobody would know if I even said it. But it's the guy who's flying the snowspeeder, trying to go find Luke and Han after they get trapped outside, right? And Han puts Luke inside the not the Wampa. That's the big scary creature, but the Tauntaun, right? You guys know what I'm talking about? The little Tauntaun. Han shoves Luke in the Tauntaun to keep him warm. Well, that morning, right in the movie, when this guy's flying out with a snowspeeder, he's trying to find them. There's a line. He says, "I found them. I repeat, I found them." Well, that was my reaction when I had it. I was like, "I found it," and I had to like exclaim it. But yeah, it was one of those things where just so frustrating. I just wanted to give up.
Does it frustrate you at all? I mean, I'm sure you have friends that aren't, as deep into physics or science or anything. Like, does it frustrate you when you can't like talk to, like, for instance, whenever I go to try to talk to my mom, right, and she's she wants to know how I'm doing, what I'm doing, and like I would love to just like give her the download, right? But it's like it's just gonna she's gonna glaze over really quick, right?
The question I always ask is, how much time do you have? Like, oh, what are you working on?
TLDR.
How much time do you have? Because I was just talking to my grandpa a couple of days ago about this pendulum, and it was pretty funny because he was like, what if you like flip the direction? And I was like, it's funny you say that because that's exactly what I did. And I kind of wish I had. But anyway, I think it's one of those things when I talk to people, I try to gauge how interested they are, because I'm sure your mom's interested in it. And there's probably only so much bandwidth she's willing to give you, right? That's like when I talk to my mom and my dad, it's like, well, okay, for about 2 minutes I'll follow along. Then you start throwing words out there, and I'm like, just nodding your head, right? It's like, okay, I'll just start shutting up now.
Let's talk about the weather.
I've got some friends who have, they're programmers. They do some tech stuff, but I don't really have too many physics-like conversations with too many people in my friend group. They mostly end up being philosophical. And there was something I was going to say earlier because we were talking about like study habits and stuff. I'm trying to remember what I was going to say. But anyway, I'll come back to that.
But I mean, that's why I'm so pumped I found Albert. I found you. Like, you guys are just so fun to talk to. And, it can be kind of hard to find those people that you can like really just go on a tangent with, right? But I get it, right? We're just deep in it, right? And I love it, and that's why I wanted to, start get it
off the ground,
trying to build Physics Society a little bit more. Try to get so
that we can find more people. That can talk about it.
Exactly.
Well, you can't do it on your own. So, I mean, you might be the most brilliant person on the planet, but if you don't have somebody else to talk to share different perspectives with, I mean, you could ask the wrong questions to get the right answers, and it's not really going to take you anywhere. But if you ask the right answers and get the right questions and get the wrong answers, that's still informative.
That's why I think it's so necessary. So necessary if you are a curious person, get into research and go to conferences.
Absolutely.
Meet more people, like-minded people. Even Einstein had like a Riemann, and like a few other colleagues, or like Newton had like, I'm pretty sure he was in the same time as Gauss or Euler. Which one of it? But
not Euler. I think would have been Gauss. Maybe, I'm not sure.
But the point is they have a lot of colleagues that they can at least mail to, or at least like travel to like talk to. Don't have any ideas.
Yeah, and I mean, I'm sure you guys know this, but UCO leads undergraduate research in the nation.
Yes.
We had you guys went to the research conference in. Where was it?
Up northwest, northeastern.
No, National Conference for Undergraduate Research. Where was that at? In a different state.
National Conference.
Is it Florida?
Oh, they went to Philadelphia? Is that what you're talking about?
Oh, you did the other one. Okay. I'm just mixing those up.
Well, I was thinking of Oklahoma Research Day.
Yeah, no.
And like there were a lot mostly UCO students.
Which is awesome. But the National Conference for Undergraduate Research, UCO had like 100 people there.
Wow.
The second highest university, I think it was like Kentucky, if I remember President Lamb was talking about it.
Really?
Had like 72 people.
That's insane.
Wow, by a large margin.
We had a large margin. The most undergraduate students at National Conference on Embedded Research.
And you know what's wild is,
awesome.
you know, we're the third largest school in the state, but from what I've heard is we're not the third most funded. Right?
Oh, not even close.
Like, we're yeah. And to know that we have that much research going on, you would think we would...
Well, I think one has to come before the other, but I think now that that's starting to kind of become more of a known thing.
Yeah.
I mean, we'll start getting some more...
One thing we would love to do with Physics Society is, you know, we have like every other week we have a talk, right? I was thinking about maybe trying to either just keep it on that same day or have... 2 weeks or every week, right? But one of those weeks is have somebody from some other department doing research in some other field, and then come and give a talk, but like relate their research to physics somehow.
Yeah.
Right. It doesn't have to be all about the physics. It can just be like them telling us about their research, what they're interested in, and then at the end just saying, and then here's you know how it relates to physics, right?
Yeah.
Because if there is that much research going on, there's got to be some interesting stuff, right?
Yeah.
Well, that's why I love research conferences, because every time I go, I don't just spend the whole time by the physics section. I like to go look at geology or biology. Right? There's so much cool. I mean, biophysics is a wide realm, right? I was having a conversation. I can't remember her name. I just met her. I think it's Dr. Messick, if I remember from biology here at UCO. Dr. Limley and I were in the hallway chatting, and she came out with all her plants on this cart. And I know nothing of biology, but I know plants are cool. And Dr. Limley and her talking about something about superconductors and how plants can like process metals or do something with it and filter metals and blah, blah, blah. And Dr. Limley was like, well, wonder if they could use these to like kind of not harvest, but kind of synthesize. Maybe that's not even the right word. Again, I don't know. Process metals for superconductors. And she goes, or we're all talking there. You know, she's like, "Well, I'm sure they could. They're really good at what they do. They can They can filter out all these metals and stuff."
Yeah.
And about an hour later, Dr. Limley turns around, and sends us both an email of some journal that they are using this particular plant enzyme or whatever to like. Yeah, basically make superconductors. Yes. I was like, that's crazy.
That's insane.
I am like so mad at myself that I haven't like taken the time to go like talk to Dr. Limley. I know he's a busy person and it's kind of hard to go and talk to him apparently, but I've seen him in the hallways and stuff like that. But he seems really interesting.
He's a really cool guy.
Yeah.
Yeah, anytime, I mean, he is busy, but just stop him in the hallway.
Yeah.
Ask him about, I think he's a nuclear physicist by trade.
Oh, wow.
So,
wow.
I'm pretty sure.
Okay, wow. So I hate to cut you off.
No.
We should probably wrap this up.
That's
it's
fine.
about 16 minutes until.
Yeah.
I just want to say thank you for doing this.
Yeah, we're so honored.
You're the first guest. So, yeah, we would love to definitely do it again sometime.
Absolutely.
Part 2 with Dr. Prather.
Yeah, exactly. Maybe hopefully this semester.
Yeah,
you know,
no, I mean,
if you have any suggestions.
we'll figure something out because I definitely want to do it again. I mean,
You know.
there's so much more I could talk about.
I mean, because you are an advisor to Physics Society, so
Yeah.
So any ideas or you know things you have to throw out at us?
Or do you have anything to say to the camera? Like,
Well, you know, I know we've talked a lot about physics, but I also love philosophy. And so at some point, I'm sure I'll find myself on a tangent of philosophy because as of late, I think I was telling you this last week, I've been taking an online class on Euclid's Elements.
Okay.
And I have a seemingly is the key word, seemingly novel synthesis of kind of logical deduction.
ooh.
And what I mean by that is, do you know what modus ponens and modus tollens arguments are?
Nah.
So they're kind of, I look at it like a 2x2 matrix. So you basically have, you affirm or deny either the antecedent or the consequence. So if I make a claim, if it rains, then the ground is wet, right?
You learn this in like digital or
Critical thinking?
Something logic.
It's logic and critical thinking, and believe it or not, when
discrete math is where
they probably do some of the truth tables and stuff in there.
Yeah.
They also do digital logic and design, similar. But I took logic and critical thinking here before I was an engineering student. I was like, oh, this is awesome.
Yeah.
It is.
But they wouldn't let it pass as an engineering credit. I'm like, this is logic and critical thinking of all things, right? Contemporary moral problems counts, but that doesn't. Anyway, so no, I mean, not to dog on that. But, I just thought it was interesting because I love logic. I love inference, and one of the things that I'm hopefully will be giving a talk on is this 2x2 matrix. It's a philosophical matrix between basically if I make a claim, if it's wet, then it must have rained, right? But that's not actually true because there could have been other things that make the ground wet. So basically you have a fog. You have an antecedent. I mean, somebody could have just, maybe their sprinkler system went off, right?
Dumped a water bottle.
Yeah, through a water balloon. But the idea is basically you make a claim, a positive claim, and then you can negate it. Null hypothesis. So I could say it rained, therefore this. You have an antecedent and a consequent. The antecedent is if this, and then the consequent is if that thing, then this thing happens. Well, in modus ponens and modus tollens, there are kind of two ways to approach a truth claim. And you can either deny the antecedent or confirm the consequent. There are logical fallacies called denying the antecedent and confirming the consequent. I think I might have said those backward. AC is affirming the consequent. That is a logical fallacy. But I put it in a 2x2 matrix because I say if instead you think about it like, okay, I can either make a claim with an antecedent, and then if that happens, then this. That's like your left-hand column. Mm-hmm. So you have an antecedent and a consequent. On the top of that 2x2 is the
deny or confirm.
Deny or confirm. And then what happens is along the diagonal, you get two valid arguments in logic. The modus ponens, which is the denying the antecedent, and then confirming the consequent is modus tollens. And that is the most powerful logical tool. It's called deduction.
Real quick, do you mind writing that out? Because I'm curious to see. I want to see that matrix that you were talking about. Because I'm trying to imagine the matrix.
You have affirm and deny, and then I have the antecedent and the consequent. And here, if I affirm the antecedent, this is good. I'm okay to do that. That's called modus ponens, NP. I could affirm the consequent, but this is conflating a necessary condition for a sufficient one. The same thing is true if I deny the antecedent. I'm actually, I'm doing the opposite. I'm saying that something is sufficient when it should actually be necessary. And that is DA. But the best thing I can do in logic is deny the consequent, aka falsification. You might remember my talk about logic and critical thinking and critical path deduction. But the idea is that if I deny the consequent, I'm basically taking on the burden of proving the null hypothesis. This is called modus tollens, MT. And that is the most powerful logical tool, but it requires something that is falsifiable. So if I say, there's no such thing as this, and I can't falsify it, well, I don't have a very strong logical argument. And if anything, I might fall into one of these. Basically, you have a fallacy on the off diagonal, and you have a truth claim on the diagonal. But it has to do with affirming this antecedent being the modus ponens. It's a valid truth claim. Valid is separate than sound, by the way. So I have a valid argument that isn't sound, but a sound argument, they're both valid. So I could also deny the consequent. But I can get into this more later because I think it's really cool. But I think basically what we'll find in my hopefully novel idea is that along this diagonal, we can represent a necessary and sufficient argument, so that if I say, that's not necessarily true, right, then I might have a special case of something, but not a general case, which I think we could kind of piggyback to special versus general relativity.
Oh, wow.
So, because I think general relativity is not
that was
fully generalized.
Totally different direction than what I was thinking. That's awesome.
Yeah.
All right,
but anyway,
we should wrap this up because you got 10 minutes to get where you're going.
Problem.
Thank you so much for doing this.
I appreciate it.
Thank you so much.
Thank you, brother.
Okay.
All right. Well, I guess.
Wait, are we recording?
Yeah, we're recording.
Okay. We can't miss this part.
Yeah, right. All right. Yeah. I guess until next time.
Until next time.
Until next time.